diesel engine, it would have ran the entire gentleman a little bit ago. Opening, it doesn't matter. So it opens, watch. Boom, closes. Why does it close quick? It captures the steam.
Welcome to Steam Up 2020 here at the New England Wireless and Steam Museum. Steam Up is an annual event held here at the museum for over 50 years. It brings together curious minds, enthusiasts, professionals, and people both young and old to celebrate the technical advances and insight brought to the world by inventors in the last 200 years. Things such as mechanical power on demand, electricity, high-tech and high-precision manufacturing, instantaneous long-distance communication, and a computer that fits in your pocket would have been inconceivable just a few hundred years ago. Steam Up highlights innovation and the genius behind it. Unfortunately, with the concerns of COVID-19, we're unable to have you all here in person, but we're pleased to be able to reach out to everyone today with the help of technology. It makes the world what it is today. The museum is located in East Greenwich, Rhode Island. We're about an hour from Boston and about 3 hours from New York City. We're in a beautiful rural setting here with lots of open space. Each year on this day, we see about 900 visitors who come to see not only the museum's collection, but the pieces brought in and shown by our wonderful exhibitors as well. It's a fun-filled day for everyone and something not seen in many places. We hope to be able to see everyone back here again in person next year, as there really is no substitute for seeing it all yourself. Our museum is entirely operated by volunteers. We have absolutely no staff at all. And honestly, we've never tried filming anything quite like what you're about to see. I hope it gives everyone some sense of what we have to offer here at the museum, and potentially something you've never seen before. Steam Up is our annual fundraiser here at the museum, and as you watch today, I hope you'll consider making a donation to support and preserve everything you're about to see. The link can be found both in the description for the video below and on the museum's website at www.newsm.org. Thank you for joining us, and now, on with the show. Let's go outside and take a quick look at the lookout boiler, kind of the heart of everything here at the museum. Creates the steam. It's our primary steam boiler just outside in the back here. Let's go take a little look and talk about that a bit. So here it is. Here is our 100 horsepower lookout boiler. It's not quite as old as everything here at the museum. Remarkably to some, this might look ancient, but this boiler is actually from 1966, and we just had it retubed about 4 years ago, so the internal wear parts are all new. And let's get into a little bit about what this is all about. This was, like I say, made in 1966, a Lookout brand made in Chattanooga, Tennessee. It was originally oil-fired. We happen to have the oil burner off that would be mounted in that area. Just had that working last year. A very interesting Venturi burner that I'm going to modify a little bit to run on number 2 rather than number 6. We tend to fire it on wood. So here, the firebox, usually a complete blazing inferno of wood, trying to heat up all the water inside. And on the outside here, we can take a look. It's really one of the most critical pieces in the museum here that somebody operate correctly as far as everyone's safety and so forth is concerned. And one of the biggest factors in the entire operation of a boiler is maintaining the correct water level inside. Now, so I guess I should back up just a little bit. This is a vertical fire tube boiler. And I think I'm going to be able to take a quick look up top so we can get a better view of the tubes themselves. But vertical fire tube meaning that the fire itself is down in the bottom here, of course, again. And the fire is what, and hot gases, of course, is what raises up through the tubes. Let's see if we can even get a quick look at them here. I don't know if the lighting is going to let us allow it, but the tubes that are here, might be able to make that out there. Fire within this chamber, and then the heat from that has to travel up through the tubes that are all surrounded by water up to the chimney there to make their way out. So the inside of this jacket here would be completely full of water, with the exception of the area that's perforated by those tubes. So the tubes keep the fire on the inside and the water jacket on the outside, and all the surface area of those tubes are what radiates the heat, transmits it to the water, and boils the water into steam. So, like I say, the inside of this whole jacket would be full of water. The water would be all the way up to the middle of the upper gauge glass there, and the two glasses that we see on that side are for visually monitoring the water level inside the boiler when it's in operation. And this array of chains that you see here are to open and close the valves on each one of those gauge glasses, either to drain it and be sure that it's running correctly, or to turn it off from the boiler in the event that the gauge glass itself breaks during operation. And if that were to happen, if the gauge glass were to break, we still need to be able to tell how high the water is in the boiler to operate it safely. So you have each one of these three valves that are over here on the side connected with the other chains. They're called tricocks, T-R-Y, so that you can try the water level, or test the water level effectively. It's another meaning for it. Not because there's three of them, but because you're trying to ascertain what the water level is in the boiler. So we've added one more additional feature in the last couple of years to make it easier for the operator. The ball here, the float ball up there, is an automatic water level monitor. So normally, this boiler operator would not only be tending to the fire, but of course checking to be sure that the water level was correct at all times, and would have to add water incrementally to the boiler. You hopefully don't want to add water in any large quantity, because you'll crash the temperature internally and thereby crashing the steam pressure. So the whole idea is to add it as slowly as possible. So we've added that feature up there to do that for us and monitor that water level. And just taking another quick look around the back, the boiler is, as I say, a real critical part because it's under pressure all the time. So you have a huge volume under pressure. Up at the top and the back, we have a couple of safety blow-off valves. If something were to go wrong, the boiler goes over design pressure rather than failing and, I hate to say it, turning into a bomb. The blow-off valves, the pressure valves in the back, would release to relieve that excess internal pressure. So other than that, we have an open steam system here. So we are feeding raw water into the boiler when we need to add makeup water or feed water. We don't have feed water return, so we're using cold municipal water pressure. And thankfully, we have enough municipal water pressure that we can do that simply by opening a valve here and letting the municipal supply push water into the boiler. Because the boiler internally is pressurized when it is in operation, you have to be able to force the water in at a higher pressure to overcome that. And normally that's done with an injector or a pump. In this case, we are blessed with the high municipal pressure to avoid that complexity, but we do have a setup here on the left for an injector. Happens to be out of place right now. So we do have, thankfully, without the visitors here today, we're not going to be running this boiler. So it lets us do a little bit of magic as far as being able to view the inside. I'm about to pull a couple of the handholds out so we can take a look at what the boiler looks like inside. Again, an area that would normally be completely full of water and pressurized, but let's work a little magic and you get to see some idea of what this actually looks like on the inside. So diving in through one of the handholds here, we've taken that handhold out and I've put a little light inside the boiler so we can see what's going on in there. Right in front of us we have all the tubes. You can only see a very small portion of them, of course. They are the water leg down in the base of the boiler. This plate on the bottom is actually the top of the combustion chamber, or the bottom tube sheet, the lower tube sheet. And again, the water leg down on the other side. You see how tall these tubes seem from inside. Of course, it's all a matter of perspective. They're only 7 feet tall. And the upper handhold that I have out there. So we'll, look around here. I'm going to get up in that other handhold and look down. But again, the lower tube sheet, these are all replaced relatively recently, so they're in good shape. Stay bolts there around the perimeter. You can see those on the outside of the boiler. But let's head out, and we can head up into one of the other handholds, the higher one here, and take another perspective look on the inside. Again, all of this would normally be completely full of water on the inside, so you'd never be able to see it. Right in front of us, the thermal plug that's in one of the tubes. It's another safety measure so that if the water level gets low enough, that plug will melt and douse the fire and relieve the pressure internally in the boiler. So we take a little look down. Hopefully I don't drop the camera here. Not the easiest spot to get into. So again, the water leg down there on the right with the stay bolts that come through to the outside. The pack of tubes will have a little better perspective up on the top because you can see all of the ends, but 205 tubes in there. So let's do that. Let's go take a look up top. Actually, while we're right here on the ladder, let's take an up-close look at the tricocks and so forth up here. As I said, the 3 valves over on the left side of the boiler here called tricocks. Not because there's 3 of them, because it helps you ascertain the water level in the boiler if for some reason one of the gauge glasses on the other side were to break. So this little scribe line right here is ideally where the water level wants to be in the boiler. And the whole idea being that through these chains from the ground we can reach it up and open the valve here. And ideally we would get steam out of the top one, a mixture of steam and water out of the second one, and straight water out of the bottom. So we know we would be able to tell that the steam was, that the water level is somewhere within this 10-inch range or so in the top of the boiler. And that's plenty of a safety factor. That thermal plug is about 2 feet down from here, so we've got plenty of room. Now on the other side, how you would normally ascertain the water level is just through the 2 gauge glasses that are here, and you can see the diagonal lines behind them. The valves on the top and the bottom are just to turn them off, to seal off each one of the passageways between that and the boiler itself from inside the boiler in the event that the gauge glass breaks. They all have a drain on the bottom. They both have a drain on the bottom to be able to flush any dust and dirt out of there, really, sediment, dirt, to be sure that you're getting a true reading in the glass. And now I mentioned that the diagonal lines on the back. Now, I believe you can just about see it here, that through the glass, the light is bent so that the white and black lines look slightly askew from the background. Well, when you have water in the glass, it bends the other way. So you get a very distinct spot at which the lines skew. And that just is a visual aid to help determine where the water level is in the glass. Now, for some reason, this boiler has 2 glasses just to extend the range of visibility. This gives us approximately, let's go from there to here, gives us maybe 18 inches of vertical visibility range. And I suppose at the same time it's also a certain redundancy, you know, so that if one of them were to break, you still have the other one to rely on. So never mind, now you have redundancy built in here as well as with the tricocks on the opposite side. And again, a little better look at the automatic float valve. There's a float inside of that round chamber that is floating in the column of water, both piped on the top and bottom into the steam, into the boiler here, and also able to be flushed out on the bottom and so forth. So now what we can do is we can go up, we'll pop the lid off the chimney, and I'll just show you the tubes up in the top to really give you some perspective on the area that those tubes take up. All right, so coming up again, we get another view of the tricocks there. We would normally have a pressure gauge mounted here. A little difficult to see from the ground. We might have to pipe in something lower at some point in time. And of course, up here in the top, one of the steam outlet valves on this side, taking off the top of the boiler and drawn down to the engines outside here. Now heading up into the top of the boiler, into the chimney section, we have this cover in place to be able to get in here and clean it out after each use. And we can really see the tubes here and the amount of space in between each one of them. So for the sake of reference, each one of these tubes is 2 inches in diameter, and you can see how tightly packed they are. As I mentioned earlier, there's 205 of them here. They're about 7 feet long, and I've never done the math to see exactly how much surface area that is, but I'm sure that's very easily done. But more interestingly, you see the space between them. You know, there's only about ½ an inch of space between the tubes in any given section. And again, all that space in between is what's actually filled with water down inside the boiler, and it gives you a great amount of contact, and there's not a lot of water in between each tube, and it really lets you conduct that heat very effectively from the tube into each one of into the water around it and boil that off. It really holds a massive amount of energy. So let's head out of here. We're going to head over to the building, the shop behind us, and we're going to take a look at the Columbia boiler. That is what we'll be running today. It's a fully automatic boiler. It is right behind us in the shop here. And the lookout, I believe I mentioned earlier, the lookout is 100 horsepower, rated for 100 horsepower. It would be just about capable of keeping up with any of the larger engines in the building if they were actually under load. Here we are in the shop building. We have a modern day Columbia boiler. It's an oil-fired, completely automatic boiler. This is what we use for demonstration purposes, if we have school groups to come by or what have you. Just do quick demonstrations at the museum. Just 2 years ago now, we repiped all of the steam lines within the steam building to seal up all the leaks, be sure that everything was in pristine condition, resurfaced a lot of the valves, and it solved all sorts of steam leaks that we had in the building. What that allowed us to do is to actually be able to demonstrate almost any engine in the building with just this little 15 horsepower boiler. And we actually learned a great deal about the efficiency of the different engines compared to some of the older ones just by doing this and seeing how much steam some of the older engines consume compared to something with the Corliss valve or the green engine or something there that consumes far less steam. So again, here we are, oil burner, fully automatic. This boiler burns oil. We have a feed water tank here on the side. So this tank is full of water, or partially full of water at all times. It's got a pump down beneath it to force water into the boiler whenever it's needed. the boiler itself has this water column similar to the gauge glass that you just saw out on the lookout. This gauge glass lets us monitor where the water level is in the boiler at all times. I can see it just there at the moment. But also inside of that water column is an electrical probe to determine where the water level is and turn that feed water pump on anytime that we need it. Also up top, for the sake of safety, up top there's a redundant probe. It's an electrical device that monitors conductivity to the water in the boiler to be sure that there's enough. Again, absolute most critical thing about running any boiler is monitoring that water level and being sure that there's enough water in the boiler to conduct away the heat at all times. Now, I want to take a quick minute because I know there's a lot of enthusiasts out there. I want to take a quick minute to talk about boiler safety. I can't say enough about how dangerous these really are when they're operated incorrectly. There's been numerous accidents through the years, even back in the day, of mills having catastrophic damage, people dying because they mishandled boilers in their operation. If you happen to be an enthusiast out there and you come across some sort of a boiler out in the wilderness or scavenged from a site somewhere, you absolutely need to pressure test that boiler with water. It's called a hydrostatic test, or get your local authority. Some cases, most municipalities, states have some type of inspection process that they put the boilers through. It just checks to be sure that the boiler can actually take the temperature, the pressure that you're about to subject it to when you light a fire inside, and to be sure that it has all the proper safety devices. In this case, it monitors the water level and so forth, and that's critical. But also, as I said about the lookout outside, a safety blow-off valve that operates at the right pressure to be sure that that actually does its job to limit the amount of pressure inside the boiler. I really can't overstate that enough. Everything needs to be tested. By absolutely no means did you find something that you don't know anything about, fill it full of water and light a fire in it. It's a terrible idea, and you're really asking for trouble. So this is real simple. Takes almost nothing to get it going. That's why this is here. Simply flip a switch, power it up. You can actually see the water level rising slightly in the glass to satisfy the demand. That was the feed water pump there. Now all we have to do is simply flip on the burner control here, reset the safety device, and the burner starts. So that's all we've got to do. Otherwise, this boiler is completely automatic. It fires itself, runs itself, checks on itself, and will shut down in the event of any conditions. So let's head over to the steam building here for just a minute. I'm going to do a quick introduction and then get started demonstrating some of the engines. So as we enter the back of the steam building here, we see the Fitchburg engine, which we'll be showing you in just a matter of a few moments, as well as the New York Safety. We have a Bullock generator here in the corner, and a whole array of other large reciprocating mill engines. Now I know that so many people here in the audience might be seeing these things for the very first time. And when I say the word steam engine, this might not come to mind at all. You know, some people might, with these things having been buried in the basements of mills and factories, undoubtedly people have never seen anything like these before. And I say steam engine, undoubtedly you think of something very different. This would be more familiar to a lot of people as a steam engine. And understandably, this is out in public view, seen for 150 years and traveling around the country, around the world, and a more visible type of steam engine. But actually, when we get right down to it, this is very similar to what we're seeing here at the museum. We were just outside looking at the boilers, And a locomotive, which would be the more proper term for this rather than steam engine, is two things in one. So at the top here, if you can imagine this locomotive on its side, this section here is incredibly similar to the lookout boiler that we just looked at. Basically just a big giant boiler with the firebox here at the end, heating through tubes, a column of water, boiling steam, and putting it back in its standard orientation. Right here at the front of the engine, we see a piston valve, a power cylinder, and a flywheel, connecting rod. These are all the same parts of what we see here in the museum in these stationary mill engines. So we're going to get into that, talk a little bit more about the history right now. One of the things we like to talk about here at the museum is really how recent all of these developments have been. I'm sure people look around at these things, locomotives and so forth, and they think of it as incredibly primitive technology. It's not true at all. Technology has evolved incredibly fast in the course of the last 200 to 300 years. I want to give you a little bit of background here. I say 2 to 300. I'm sure it seems like a long time for a lot of people, but the development was actually very slow initially. Since that time, we have absolutely exploded with technology, and our understanding of technology, scientific principles, and so forth. I know when I was in school, I couldn't have told you the difference between, time period-wise, I couldn't have told you very much difference between Archimedes and Galileo. They both sound incredibly old to me. You get right down to it, Archimedes was about 250 BC, and Galileo would have been around 1600. There's 1800-year difference there. I couldn't tell you the difference. Archimedes was doing math, he's doing engineering, he's doing astronomy, he was a scientist. So, and of course, kind of relating to the steam engine, back in that time frame, around that 200 BC period, they had the Aeolipile, or the hero's engine. People might be familiar with that. I'm going to disturb my drawing here a little bit. The hero's engine was the sphere with the two little jets coming off of it on opposite sides, with the bowl of fire underneath it that would just spin around with the steam escaping from the nozzles on it. So 200 BC, they had that concept, but they couldn't make it do anything. It didn't really do any work. And despite Archimedes and 1800 years of having that type of technology, it wasn't until 1712 and Thomas Newcomen that it really started to do some work. I mentioned Newcomen. He's a bit of a predecessor to what we see here as a steam engine. The standard steam engine of today is typically credited to James Watt later on in the 1700s, but as a progression here, Newcomen came up with the first very functional way of turning heat into work. It's pretty significant. To that point, the only way that you could physically generate work was via the wind, human power, or animal power. Newcomen came up with a very simple system here. He didn't actually understand quite why it worked, because they didn't have the scientific understanding of everything as we do now. And again, we're talking 1712. He had built upon, I think it was Thomas Savery with his pumping engine or water pump. It was also fire-powered, but not nearly as effective as even the Newcomen engine. And again, maybe point of reference around this time frame and scientific discoveries, Boyle's law, the idea of gravity. Sir Isaac Newton didn't really devise the principles of gravity until the very late 1600s. So I know personally, in school, all of that stuff seemed like ancient history. It's really not that old. So in the Newcomen engine, it relied on atmospheric pressure to do its work. Very simple here. He had a tub of water, or a big vat of water with a fire underneath it, generating steam. He could fill a cylinder with steam and then close everything off in the cylinder, put a spray of water into it to make the steam condense back into water, and as it was drawing a negative pressure here in the cylinder, atmospheric pressure would push the piston down and raise the weight that was on the other side. He would then have to open the valve here again, letting the weight take over, pull it down as it sucked steam from the boiler effectively into the cylinder again, and you could start the process all over again. It was incredibly inefficient because the entire thing had to be heated and cooled alternately for every single cycle, but it worked. It was the first time they had managed to accomplish such a thing. And simple things, we had water up at the top here for the sake of sealing the piston. They didn't have the manufacturing capability of making a well-fitting piston. As I say, it worked. It operated at atmospheric pressure. The boiler itself didn't actually apply pressure to the cylinder at all. It was all about atmospheric pressure pushing down against the displaced air and the negative pressure created by the condensing steam inside. So, despite seeming like an incredibly primitive thing, which it was, it helped spawn the ideas for the modern day, or the evolution of the steam engine, done by Watt. This type of principle existed for about 80 years, 70, 80 years before Watt managed to improve upon it. Again, he didn't actually understand, Newcomen didn't really understand exactly what was going on in there. They just found a series of principles, a series of things that worked as one, and they put it to commercial use. We do have a demonstration that I'll do for you guys later on about the power of that atmospheric pressure. You might think it isn't very effective, but I can show you later on that it's incredibly effective. So, approximately 70 years later, James Watt, for whom, of course, the electrical unit of energy is named, the watt, makes some very significant improvements upon the Newcomen engine. It took him about 30 years to make incremental improvements upon the Newcomen design. He first started by, I believe, the first thing was the external condenser. So Watt invented the external condenser. By virtue of not having to condense the steam within the cylinder, he then didn't have to heat all the metal of the cylinder and the piston back up again. So that was one initial improvement. Later on, of course, managed to actually put pressure into the cylinder. By making it double acting, he sealed the top end of the cylinder here so that you have a negative pressure being drawn in by the condenser and pressure being applied by the boiler, now external to the equation, to the opposite end of the piston, pushing it up. He still had the rocking beam that Newcomen had. He had to devise this parallel link motion here to keep the piston rod in a straight line, vertical, as the rocking beam went through its motion. He also, again, implemented the flywheel for the sake of keeping the motion smooth and, smoothing out the transitions in direction that were going on here. But he ran into a patent issue. Someone else had already invented and patented the crank, so he had to get around that by using a sun and planet gear. I don't know off the top of my head if he invented that, but he was able to implement that to get around the other patent. So there it is, the basic improvements that Watt made to the Newcomen engine and the predecessor of all these things here. So the technology evolved very rapidly thereafter. Once Watt invented this and made these improvements to the initial Newcomen design around 1780, in the course of the next 20 or 30 years, he continued to improve upon this for the sake of stationary steam power, but then by 1810 or 1812, Richard Trevithick invented the steam carriage and the locomotive, at least the predecessors thereof. So around 1810, the locomotive came in, and again, we looked at the picture of the locomotive. I know people think of that as incredibly old, but realistically, there was no such thing as a railroad or a locomotive prior to 1812, 1815. And of course, then all this technology, the development, the expansion of the railroads around the world, the implementation of all the industrial mill engines, the improvements to the valve technology, all that stuff went on within a very short amount of time. The course of the next 100 years was it for all of those things before being supplanted by electricity and everything that we have today. I hope you see that technology moves very fast, and I haven't even touched upon the radio technology, but we can get into that a little bit later for the sake of electricity having been invented and Morse code, wireless communications having been invented in 1880s, 1870s, and only really implemented into the seeing implementation into the very early 1900s, and then to go from sparks and electromagnetic disruption in the air in 1900 to a cell phone in everybody's pockets just 100 years later. The advancements have been incredibly rapid, and it has completely altered life as we know it today from what it was just 150 or 200 years ago. People really need to have more appreciation of how different life really is today from just a short time ago, thanks to these improvements. Now let's get on with the rest of it here. We have Ernie waiting for us over in the corner there to show us the New York Safety Engine.
Well, we're here today with the New York Safety Steam Engine. This engine was built here in Rhode Island, manufactured, and it went to the Rhode Island Agricultural College. And it was one of its 3 primary power sources when the college began to have electricity and electrification. Let's talk just a little bit about a New York Safety Steam Engine and Rhode Island. I did say it was built here in Rhode Island. Well, there's a little small town west of here that we'll talk about a little bit more. But first of all, manufacturers years ago tried to use names and office locations that were worldwide known. And here we have a New York Safety Steam Engine. Well, this engine was built in Hope Valley, Rhode Island. Hope Valley, Rhode Island is a small town on the Connecticut-Rhode Island border. Who in the world ever heard of a Hope Valley Safety Steam Engine? Whereas a New York Safety Steam Engine, big difference, especially for advertising. Let's talk just a little bit about steam. What is steam? Why was it used? And so on. Well, we get steam by heating water in an enclosed container. The pan on your stove, when you heat water in it, you see steam coming off it, that's really water vapor. To get steam, it needs to be enclosed. You now have steam captured in an enclosed container. And that's what steam engines were all about. They used that pressure. When water turns to steam, what does it really want to do? It wants to go back to atmospheric pressure. It wants to turn back into water. Whereas it was about 1,700 times greater pressure than atmosphere. And from that point on, these engines used that. So, what happens here? The steam is piped from the boiler, where the steam was made, to the engine. Piping here. And steam engines had to be preheated, because stop and think for a second. Is water compressible? Water is one level above a solid. Steam is 2 levels. It's water turned into a vapor or a gas. So this engine is already fairly warm, so it started easy. Notice I did have to turn it. I'm not letting it do any work yet. And as it slowly gets warmer, and it is, we can bring it up to speed. Notice that it's completely quiet. Steam engines notoriously made very little noise. It's the term external combustion. Your lawnmower, your car, your boat, those are all internal combustion. The explosion, the heat source, and everything happened in the combustion chamber, in the engine. Here, with external combustion, the boiler is elsewhere. It's turning that water to steam, and it's then piped in here, as we said previously. A powerhouse using steam would have been almost silent. Let's quickly talk a little bit more about steam. Why is it that manufacturing industry and generally went to steam? Previous to steam, how were mills powered? Predominantly by water, with a dam, a water source with good fall or waterfalls or height of water above the mill. So predominantly mills used to be in river valleys. There was a lot of that in Rhode Island. Rhode Island's always been a big state for manufacturing. With the advent of steam, if you had a source of water, now when I'm talking about a source of water, it could be a pond, it could be a well. It did not even have to be running. That water was pumped into a boiler, turned into steam, and it ran a steam engine. At that point in time, you could put a mill wherever you wanted as long as you had a source of fuel. It could be wood, it could be coal, it could be oil, and you had a source of water. It could come from a pond, it could come from a well, it could come from a very slow-running brook or river. So consequently, if you look at the history of Rhode Island, early on, mills were located in river valleys. With the advent of steam, a lot of, or most of Rhode Island's manufacturing was in Providence, or one of Providence's suburbs. So we talked about the New York Safety Steam Engine and why it wasn't a Hope Valley steam engine. And in reality, the company was Nichols and Langworthy. Rhode Island's historical manufacturing is incredible. The little town of Hope Valley, Rhode Island, if we look at it today, there is actually part of one of the buildings from Nichols and Langworthy, aka New York Safety Steam Engine Company, but the great majority of it actually burnt down in the early 1900s. The other thing that's a little bit interesting, Nichols and Langworthy had started to manufacture gasoline or internal combustion engines. The gasoline engine factory was the part that caught fire and caused the entire facility to burn down. History says the employees went to lunch one day. When they came back, it was all gone. Wow. That had to be horrible.
So what you were saying, Ernie, New York Safety versus, what was it, Nichols and Langworthy?
Yes, sir.
I'm still not, that whole thing was a marketing scheme?
Yes, sir. And I don't want to pick on a small town in Rhode Island, but remember, manufacturing could very well go worldwide, indefinitely. Would you, as a person buying an engine for a factory, a mill, even maybe a home and domestic water supply, because these things came in all sizes, from little tiny to flywheels that were 15, 20, 30 feet in diameter, would you buy a Hope Valley safety engine or a New York Safety Steam Engine? Which one sounds like you're going to have a better product?
You know, I suppose one thought that I just had while you were saying that is this was new technology at the time for everyone. You know, potentially people were had their water wheels. You know, they had seen that technology for hundreds of years. They were used to powering their factories one way. In some cases, this might have been their very first steam engine. They're finally going to embrace some sort of a new technology and change over to this brand newfangled thing, the steam engine. And I suppose exactly like you're saying, the New York Safety Steam Engine Company sounds a lot more recognizable and meaningful than the Nichols and Langworthy Company or the Hope Valley Safety Engine or something. So perfectly understood that it's a comfort thing for people, I would imagine.
Oh, absolutely. If you look at the history of Providence, like a lot of the Northeast, there were manufacturers of silver products, silverware, jewelry, and so on. And there was a silver company in downtown Providence, or the Providence area, that originally was on a mill pond. If I say mill pond, what does that bring thought? Does that make you think water wheel, water power? To me it does. Well, as they got bigger, because industry prospered very easily in that time frame, they built a factory right in downtown Providence. And they went from water power to about a 400 horsepower steam engine. Wow. Now, previous to that, they did have a steam engine, but it was only 50 horsepower. Well, 50 horsepower is pretty big. This one's 25. However, they also bought a name brand steam engine. They were in Providence. Providence, one of the major engine manufacturers, was the George Corliss Company, and guess what? They bought a George Corliss steam engine. And just think of the transportation costs. They're in the same city.
Yeah.
What transportation cost?
You know, something I was thinking about just a short time ago is the growth of industry around the New England area. So all the textiles really being some of the first manufacturing that went on in this country. You know, the first industrialization was all around textiles. And all that boomed between, around the Northeast really, but typically right around the Rhode Island and Massachusetts area. So it only made sense that all the support technology, all the development of steam engine stuff went on in this area. And then as that industry allowed, because they developed all this technology, allowing manufacturing to go on anywhere that it wanted to, anywhere you had a source of fuel, then that industry could spread to the rest of the country. So we basically, you know, steam engine companies built themselves out of business. They developed technology that could work anywhere, and then as industry moved to the rest of the country, so the transportation costs were minimized, steam engine manufacturing went with them to follow the industry across the country.
Well, Randy, let's talk about what you just said, and I'm going to take part of it as kind of a question. Well, but let's just talk about that twofold first. We talked about industry and how they moved from a water power source to being able to have a mill or a factory virtually anywhere. And Randy did mention Massachusetts, so I'm going to take license with that. Lowell, Massachusetts was really big in textile. If you go to Lowell, Massachusetts to this day, there's actually a national park there, and it's almost all textile. And guess what? It's almost all water powered. Their system of canals, even locks so they could still move boats through the area, is absolutely incredible. So Lowell is northwest of Boston, more north, but anyway. Then let's talk about the area of Fall River, Massachusetts. Also a huge textile area. And guess what? They don't have any running water. They're on salt water. They're at sea level. How did this happen? It happened with steam power.
Ernie, do me a favor. Let's shut it off and kind of go through some of the parts and pieces here so people understand what we're actually looking at.
All right. A lot of the pieces here, when you're driving your car down the road, they're there. You can't see them. That's one of the reasons that folks all have a fascination with steam engines, myself included, because it's external. Okay, does your car have a flywheel? Yes, your car does have a flywheel. It's probably nowhere near as large and heavy as this, but what it does is it smooths out power impulses. It stores inertia to help put torque from the engine into a belt to drive a generator in this case. Does your car have a crankshaft? Absolutely, so does a steam engine. And you can see these discs in here turning, and you'll notice that hooked to the crankshaft is a connecting rod. You can see it moving back and forth and kind of up and down. That connecting rod, now here's something that's unique to most steam engines, is something called a crosshead. Notice that it's just sliding back and forth. It has no angle like the connecting rod does. And on the front of the crosshead is a piston rod. That piston rod is moving in and out of the back of the cylinder. And it's a perfectly straight line.
Now,
Okay?
I know there's a reason for that, Ernie.
Okay, well,
Why do we have to separate it?
all right. It's a perfectly straight line, and in your car, the connecting rod, once again, notice the angles.
Let me swing back over that way so we can see here.
Notice those angles. Those angles put side forces on the piston in the cylinder. We'll talk about a cylinder in a second. That's not a good thing. So the designers from way back when, they never even thought about that. All they wanted was the piston to go perfectly straight in and out of the cylinder. Plus the fact of, unlike most internal combustion engines, yes, there are some that are what we're going to call double acting. What in the world is double acting? Well, that piston rod hooks to a piston. That piston right now is back here. We're going to admit steam with this valve, we'll talk about that valve in a second, and push the piston that way. Now the piston is over there. We're going to admit steam to that half of the cylinder with that valve and push it back this way. Since the piston is nothing more hardly than a disc, sometimes a pretty big disc in a steam engine, it truly needed to travel straight in and out. Let's talk about the valve for a second. Every engine has to have some sort of valves. This particular engine uses a piston valve, piston meaning it's round, and also notice that this valve travels perfectly straight. And so right now, the piston is here.
The cylinder piston.
Yes, sir.
Gotcha, okay.
Now, as I move the engine further, you'll notice this will move,
And that,
and when
the
it
valve.
moves, that is a valve piston.
gotcha.
Okay? It's going to move and it admits steam. See it move?
So that's moving opposite,
And what that did is that opened a passage basically from this pipe right here
okay?
into this side, this end of the cylinder. And it's now pushing the piston here. We're going to admit steam into this end of the cylinder. See the valve move? And it pushes the piston back here.
Gotcha.
Now that we're here, it's going to repeat that one more time. Notice the valve will move. It's admitting steam here and it's pushing the piston that way. All right, we admitted steam. We need to get rid of it. I guess that would be an exhaust valve. So this engine, or this style of steam engine, actually uses the same valve to admit steam and the same valve to exhaust steam. So when it's admitting steam over here, it's exhausting steam over here, and that happens in this chamber.
All through the same mechanism.
All through the same mechanism, and somewhat slowly. In other stories and informational videos and so on that we have, we'll talk more about steam engine technology, but right now, we just want to get into the basic functions of a steam engine.
All right, great.
Let's start a big steam engine, then we'll talk more about it. It's the same thing that we just looked at with the New York Safety Steam Engine, but bigger. The same pieces are all here, and maybe more of them. With the New York Safety Steam Engine, how did we start it? I physically turned the flywheel. That's not going to happen here. So what I'm going to do is manually operate the valves. Remember we talked about admission valves and exhaust valves and so on? So
If you had to guess, Ernie, I know we're looking at the valves here in a minute, but if you had to guess, what do you think that flywheel weighs over there if we were to try to turn that around by hand?
that flywheel probably weighs in the area of 6 to 8 tons.
Okay?
So, no, I'm not going to turn that. If we do get in a situation where we have to turn it, it takes 2 or 3 of us.
Okay, great.
All right.
Thankfully, we have steam power on our side.
Yes, we do. So what I'm going to do is manually operate the valves. And that was almost too quick, but did you see that I operated a lever right here, and this lever is now operating automatically. Once the engine had moved through this device right here,
Hope we catch it. Oh, just caught it.
and I relocked it again because it came loose, that allowed me to manually start the engine. Now, this is just a storage place. Once again, I essentially did with this lever what the engine is doing automatically.
And now by virtue of locking this in here, it's running automatically. It moves itself.
So if you follow this rod back towards the crankshaft, you'll see this rod is being operated by
Gotcha.
2 eccentrics.
Okay.
All right, let's go over items on this engine quickly. We talked about most of them. It's a lot bigger. We'll start with, we talked about the flywheel, a couple 100 pounds versus 6 to 8 tons. We talked about the governor. Here's the governor. Looks somewhat similar, it's just separate from the flywheel. What was the governor for? To maintain a specific speed and/or speeds.
Oh, you know what? I didn't say it earlier. I got it. Cruise control.
Yeah, cruise control for a stationary engine.
Nice.
All right, the governor is actually causing this rod to change its position in small increments to regulate speed. This rod, if you follow through, operates this, and you can see not 1 but 2 admission valves operating. Remember?
Just like you were saying earlier, so this is actually operating and admitting steam to one end of the cylinder, and then the other one sends steam to the opposite end of the cylinder, just like you were saying on the smaller one.
Yes, it is. And remember, we talked about the piston as a big disc. This is the middle. It moves from here, it gets pushed this way, then it gets pushed that way. It's referred to as double acting, meaning it's pushed in both directions.
Or I suppose, I've never actually heard it referred to this, but of course, cars and internal combustion engines are typically 4-stroke. Anybody understands what that means? You get 1 power cycle every fourth stroke of the, not every 4th revolution, but every 4 movements of the piston. This would be a single stroke because you get it every single movement of the engine.
Yes, this is a 1-cylinder engine that produces 2 power strokes per revolution.
Nice.
All right.
Let me swing around the other side so we can see what's going on over here. Real interesting ornamentation they were doing on things at the time. Well, this is a little warm here, Ernie. It's not steam temperature. What? This seems real thin. What's going on with this?
All right. In New England here, we're not quite so concerned with insulation in your house in the summer. But in the wintertime, what's your oil bill going to be with no insulation in your house? That'd be pretty steep, right?
I don't want to find out.
So what they did, because we talked a little bit about steam. Remember, we heat water in an enclosed space, right? It turns into steam and it makes pressure. All right? We want to keep that temperature and pressure, laws of physics, they go together. The higher the pressure, the higher the temperature, and vice versa. They go up and down together. We want to keep the temperature of this as hot as possible. Steam engines are internally cooled because as the steam expands, remember, steam wants to go back to atmospheric pressure and water. So the longer we can keep it hot, that means the more pressure we can keep in here. So this is called lagging. And inside it, when this engine was built, it was probably full of horsehair for insulation.
Gotcha.
So,
I actually see, now that you're talking about insulation, I see that the piping here is all insulated as well, and I suppose that's for the exact same purpose, to try to keep the energy inside instead of wasting it away.
it's right back to that laws of physics. The higher the pressure, the higher the temperature. So if we work it the other way, the longer we can keep the temperature high, the longer we can keep the pressure up, so that the engine gets as much of it as possible to convert into energy.
Interesting. Makes a lot of sense. So I see all these, again, bits and pieces. This is basically the same as the one that we just looked at, just larger and, you know, obviously physically easier to see. I didn't really notice any of these on the other engine there, but certainly a number of them here. What's that all about?
All right, we'll go back to your car. Every once in a while, in my newer cars, you probably get that nuisance wrench light in your dash saying, oh man, I gotta take it to the shop. And it might be something as simple as an oil change. Well, these engines were lubricated by things called oilers. These were manually filled. The amount of oil that was being delivered was adjusted by turning this knob and looking at how often it dripped.
You see it there. Nice.
So what happened to that oil? It's called complete loss. We have ways to capture that oil because we try to be environmentally conscious, but the oil basically goes through the engine and goes into a catch pan on the bottom. And you'll see them all over the engine. When we get back to the other end, we'll talk about another one that lubricates the internal part.
Gotcha.
Once again, here's the crankshaft. This is referred to a disc crankshaft. Connecting rod, crosshead, piston rod. Notice only the connecting rod gets the angle. The piston rod goes straight in and out of the cylinder to keep wear and sealing, wear to a minimum, and sealing as good as possible.
I get it. So this actually makes a lot more sense in the bigger scale because we have pressure inside of here on the pushing the piston the opposite way, you have to keep that rod straight so that you can seal it there. And they're not really worried about that in an internal combustion engine where you don't have pressure on the backside of the piston.
That's exactly the case.
It makes a lot more sense when it's in bigger scale right here.
How would I keep this angle sealed over here? There is a seal in there.
Exactly.
So
Makes sense?
let's walk back around the other side.
Just take a quick look over here while we're at it, Ernie. Interesting builder's plate.
All right,
Neat stuff.
it's a Fitchburg steam engine. This engine was built, obviously, in Fitchburg, Massachusetts. The company was big enough, I guess they didn't worry too much about being a Boston Safety steam engine or something like that. This engine had a rather unique history. It went all the way from Fitchburg, Mass, to Peterborough, New Hampshire, in a straight line, maybe 20 miles. It ran a humongous loom. That loom was used for part of making paper currency in years gone by. That whole procedure changed. This engine became surplus, and it was donated to us here at the museum by a friend of the museum who actually grew up in Peterborough, New Hampshire, and knew all about this engine. This is, I believe, the first or second big engine here.
Gotcha. So these parts here are definitely a lot easier to see than they were on the smaller Nichols and Langworthy, the New York Safety engine over there. Ernie, want to just kind of point out what we're looking at here?
Okay, notice how this and this are running perfectly true in a perfect circle. Notice how these are actually kind of walking, in this case, up and down or in and out. They're, as I mentioned earlier, called eccentrics, and they're actually what are causing the valves to admit and exhaust steam. Wait a minute, valves to admit and exhaust. On the New York Safety steam engine, one valve was doing it all. This engine has admission valves that are operated from this one and exhaust valves that are operated from that one. That allowed the designer manufacturer to manufacture an engine with much greater efficiency.
So they're able to move that and, alter, kind of fine tune it a bit? Is that what you're thinking?
Okay? The governor does not need to have any effect on the exhaust valves. It needs to have the effect on the admission valves. So they're completely separate. The governor in here can change the travel on this one. to emit more or less steam depending on speed. This one is just here and it is what it is. Doesn't need to change for efficiency. Just a quick note on efficiency. Steam engine efficiency, in the best case, only, well, not only, it never made 10%. And most of our electricity today, if it's not solar, comes from steam. What? That would be a steam turbine. They're extremely efficient. They can use the steam multiple times. And I'm sure most of us out there are getting our steam from one of three places now. Hydroelectric, steam turbines, wind power, and the newcomer is solar. More and more we're all seeing solar farms.
So I'm not following you here, Ernie. You're saying a lot of electricity is still steam powered. What about all the nuclear power plants and, you know, cogen plants and so forth like that? I mean, that's totally different.
Well, you mentioned cogen. I'll go there because I can give you a reasonably good answer. And hopefully it'll be clear and concise. A lot of places you'll see little short, stubby smokestacks, usually 2 or 4. And that goes with the word cogen. Smaller power plants will use like a 747 jet engine running on natural gas, so it's clean. Well, if you take a jet engine, what comes out the back of the engine? Heat, a massive amount of heat. That heat goes into a boiler and makes steam. So you've got this giant jet engine running on natural gas, so it's environmentally sound. That heat goes into a boiler and makes upwards of 1,000 psi of steam. That steam is then put into a turbine, steam turbine, that's on the other end of the shaft that the generator or the jet engine is on.
So they're using the waste heat to generate more power via a separate turbine.
The key point there is you said waste heat. I don't want to correct you, but the idea is trying to make sure that we don't have any waste heat. We want to make sure when all is said and done, there's nothing coming out of the smokestack, not even warm air. And a lot of these cogen plants have the ability to come very close to that. And once again, you've got natural fueled jet engine, so it's clean. You think of those horrible smell when you're at the airport when they're running on jet fuel. You're running them on natural gas, they're clean, environmentally sound, then we make steam off the exhaust so we don't have waste heat, and we're running a steam turbine. Steam turbines are efficient for several different reasons. I mentioned they use the steam multiple times, 10, 15, 20 times. And how do they do that? It's simply a matter of the diameter of the turbine. If you ever see one apart, it's a big cone. High pressure steam goes into the little tiny end of it. As the steam pressure gets less and less, the cone gets bigger.
You know what? We have something just like that around here. I know, I'm just thinking of it. I think we're going to get to that one a little later.
Right.
They used to do something similar, but got it.
The point of it is, the big thing with the turbine, it spins. Think about it. You put a box fan in your window. What does that fan do? It spins in the same direction as long as it's on, correct? Look at this. Stop, change direction. Stop, change direction. This is reciprocal motion. In every 1 RPM or revolution, this thing changes direction twice. That's very inefficient. Think what's happening in your car at 8,000 RPM with 8 cylinders.
A lot of parts and pieces moving in multiple different directions to generate the actual power that you really want.
How did something like this engine run a mill?
You tell me. I couldn't tell you.
Okay. What does this look like? It's a flywheel, I know, but what does it look like? Does it look like a big pulley?
I suppose you're right. I suppose it does.
There would have been a very large belt made out of leather, this wide, that came off here and went to something called line shafting that ran every part of the mill. So most of these, you won't see gears or anything else. It was just a big belt that ran off of this. This is nothing more than, I said it was a flywheel, but it's also a giant pulley.
Interesting. All right, I hate to say it, Ernie. I think we need to wrap it up over here and move on to the next thing. I know there's always a lot more to tell about these stories, and hope everybody will actually come by and see some of what we have here. But yeah, we'll have to get back to this one at another time. Thanks for a little talk on this one. We'll catch up with you in just a little bit about one of the other ones.
Thank you.
Thanks, Ernie. I just want to take a moment to say thank you for joining us here today. This video is being presented in lieu of our 2020 Steam Up here at the New England Wireless and Steam Museum. Steam Up is our annual fundraiser here at the museum, held for over 50 years. We wish you were all here in person, but we're also very excited to open up our collection to the online community and enthusiasts around the world. We hope you're enjoying everything thus far and would appreciate your consideration of making a small donation to the museum today. Every dollar you donate goes directly toward the continued preservation and display of everything we have here at the museum. We have absolutely no paid staff, and everything is operated by volunteers. A link can be found in the video description below or on the museum's website at www.newsm.org. I hope you'll consider helping us in our efforts with a generous donation today. Thank you. All right, let's head over to the wireless building here. I know Craig's waiting for us to give us a little bit of background on early wireless or early Morse code technology and so forth. Right, Craig?
Yes. Morse code is the original text messaging, and it's exactly that because with the advent of what's called a sounder, we could actually send messages. This is all has to do with Samuel Morse, and you've heard his name. Samuel Morse was actually an artist early in his career, but in the back of his mind he always had the idea of an electric telegraph for instant communication, because prior to that it was horseback or mail going from here to England taking 12 days on a ship. There was no instant communication except for smoke signals and things like that. So
what was this? There was some sort of story there, Craig, right? That
yes.
Something inspired him to...
Yes. Samuel Morse, being the artist, was painted a lot of public figures, political figures, and he was doing a portrait of General Lafayette at the time, and he got a letter on horseback saying that his wife was ill. So he immediately dropped everything and headed for home. When he got home, his wife had died and was already buried, and that all due to the lack of instant communication. It was just a very terrible thing for his life.
It took such a long time for that message to get to him,
right.
and then him to actually physically get back that
right.
she was already dead and buried,
right.
and
right.
Interesting.
So that gave him renewed energy to work on his idea of the electric telegraph. So he abandoned his artwork, which wasn't really making him enough money anyway, and he created, along with Alfred Vail and Friedrich Gurk, the three of them really were instrumental in creating what we call Morse code today. With dots and dashes representing numbers and letters. And with the electromagnet type of setup that Alfred Vail created, the sounder and wires and battery power, we were able to communicate instantly across distances, wired telegraphy. So the longer the wires, the further you can communicate. So in 1844, that was the first real telegraph message that was sent from Washington to Baltimore by Morse, which was "What hath God wrought," which is ironic. So that made everything happen, from everybody wanting to have instant communication across the country. So within 10 years, we had wires stringing along railroad lines, and businesses were booming because they had instant communication now, which they didn't have before. So anybody who was able to install telegraph in their homes or in their businesses, they had instant communication.
Now, I was thinking exactly what you were thinking a second ago, being strung up along the railroad lines. That was actually an important part from both a timeline standpoint, and they just happened to be kind of evolving at the same time.
Right.
And it actually came into great use to schedule trains, increase safety around the railroad lines and all that other stuff, right?
Absolutely. You could communicate when trains, because they very often only had one track, because it was expensive to make railroad tracks. So they could communicate much more easily now. A train is coming, and avoid collisions and things like that. Also, Abraham Lincoln was really instrumental in using the telegraph. He converted the library of the White House into a telegraph office, and he used it daily to find out what's happening during the Civil War.
He was out there text messaging away from
He
the
was.
from the library in the
He
White
was.
House.
He was. And some Lincoln experts sometimes bypass that information, but it's really really important. He was on top of it.
Just talk a little bit, because I don't really see the connection between text messaging and Morse code. I mean, this seems like such primitive technology. What?
Well, it is. It's simple, is what it is.
I hate to put you on the spot, but I know there's a connection here.
It's simple technology, in that with the dots and dashes, we use abbreviations all the time in text messaging today. Like CUL means see you later, and you can do that with Morse code as well. Here's a C, U, L, and we're text messaging. So somebody who's copying this down, you'd have an operator listening to this and copying down the message to deliver. It would say CUL or see you later. So in effect, it really truly is the first instant text messaging device that we had.
And I know you and I have talked about this before, and you've alluded to this actually being faster. Have they done? Have you told me that they've done studies on
Yes.
this, and that the Morse code is actually quicker,
Can be quicker
than text messaging?
The main reason is when you start sending Morse code, you're sending the receiver's receiving the letters instantly. When you text message, you have to create the message first, then hit send, and by that time, a lot of the message is already gone through.
Oh, so this is the receiver is receiving the letters, the characters as it's being
it goes.
sent,
Yeah.
immediately able to start processing the message and think about what they're going to send back,
Right.
rather than
Right.
the delay of composing the
Right.
entire message, pushing send, reading it.
Right.
Interesting.
Yep. And if the response to a question is a simple yes, it can be, which is R for Roger, or C, which is another term used in Morse code for affirmative C.
We got the K. We got the K nowadays, right? Hey, K. Okay.
So it truly is text messaging. So he was on a roll with the telegraph. So what could be better than having lines strung up all over the country, enabling people and businesses to instantly communicate? What if we could only do it from here to England, or from England to here?
Once we've got the country wired up, why not keep going, right?
Simple. Why can't we just put a telegraph line across the ocean?
Interesting.
So we already had telegraph lines under rivers and lakes and ponds in areas of the country that was necessary, but that's a short trip. Cyrus Field had a dream. Cyrus West Field, one of the most persevering people in history, one of the most important people in our history, because he had the dream of saying, yes, we can put a cable across the Atlantic Ocean. It's only 1,900 miles long.
Nothing.
So Cyrus Field was wealthy enough himself and had wealthy friends. He got up enough money and permission to get 2 ships outfitted with 2,500 miles of cable all at once, and a little extra in case anything happened, and it did.
Once,
And-
twice,
and-
18
yeah,
times,
yeah.
you know.
And so the cable itself has the copper wire in the center, and then an insulation called gutta percha around the copper wire, which is from the sap from a tree in Malaysia, like plastic, so it's waterproof. And then to keep it strong, strands of iron wire around the outside, so strong but flexible. And they'd put these on huge reels and in big tanks on the ship in order to pay it out across the Atlantic. What could go wrong? You think about it.
Sounds like they've got it all worked out.
All worked out.
Yeah, just spool the stuff out and let it lay along the floor of the Atlantic, and everything's perfect.
Now there, you see larger pieces here, but when it got to the shore end of the cable, they had to increase the size because of rocks and things like that. So, But so what could go wrong? So they set the ships out, and they're planning on going from the west coast of Ireland to the east coast of the United States, which the shortest point is in Newfoundland. And they got not too far out, and the cable on the back reel started paying out really fast with no explanation. It just started zzzz, and they were like, "What's happening?"
Really deep spot in the ocean?
Exactly. Exactly. They weren't going any faster, but the reel was zipping along, and it was becoming dangerous. It was just paying out too fast. So one of the crew members hit the brake on the rail, and the stern of the ship started to go down. It was that much tension, and it snapped the line.
Snapped the cable. Oh, wow.
So they lost that. So that was a failure. That was try number 1 or 2, and several tries. I mean, this is a big venture, and Cyrus Field just didn't give up. It's just redefining the word perseverance. And again, he had to get funding, he had to get permission from Congress, and he got more funding, and I believe it's the 5th time, they said, okay, we're going to do this right. This is probably the last chance we have. And they had 2 ships, and they met in the center point between Ireland and Newfoundland, and they spliced their cables together, and they worked their way towards each coast. Ironically, the electrical field that was produced, they communicated through the cable, ship to ship, while they're paying us out at certain points.
Interesting.
But the electromagnetic field from the cable threw off their navigation compasses, and they both veered way off
Oh, boy.
course. So again, something that was unforeseen. But they eventually get it laid, and Queen Victoria sent the message to President Buchanan, congratulating. It was 93 words, and it took 17 hours to get that message across. And it doesn't sound like instant communication.
Certainly doesn't sound like instantaneous communication to me.
You think you're going to hear clickety-clack or dee-dee-dee-dee-dee-dee? No. After 2,000 miles of cable, you're going to see a needle on a little galvanometer go. That could be an E. Is that a dit or a da? So let's wait and see if the next one's longer. It would take up to 2 minutes to get one letter, and so it took over 17 hours to get this message. But a lot faster than a week or 2. So it's still considered, for this long distance, it was still considered long distance.
Very interesting.
Of course, today we have fiber optic cable, which information can travel through that at the speed of light. So it's a huge, huge difference.
I suppose they didn't actually know or expect that it was going to take so long, and I know I've heard a little bit of the stories about what happened with that first cable.
Oh yeah. It took months, and it's really fascinating to think that they had a crew of, believe it or not, about 500 men on this ship.
Wow.
And they had to eat, because this was going to be months. They brought livestock with them. They needed to eat, so they needed to be fed, and just a huge, huge undertaking. And very interesting kind of cruise.
Yeah. Now I know we got to move on here, but I know there was a little story that first, after all that time, all that work, the 5 different trials and everything else, they finally had a cable that worked.
Mm-hmm.
It took 17 hours to get the first message across, and on and on. How long did that cable last?
I think that one lasted less than a month.
I knew it was a short amount of time. I didn't think it was that short an amount of time. But if I remember right, they were trying to get the signal through. They didn't realize how difficult it was going to be, so they're trying to push a signal through. They kept on cranking up the voltage and higher and higher and higher.
Right.
And then...
Well, they started with like 600 volts. This
nothing.
voltage is coming from batteries. There's huge, huge battery banks that they made. And so one of the engineers said, let's push the voltage. And there's some disagreement, but they did it. And they pushed through 2,000 volts, and eventually burned out parts of the cable. So
Unbelievable.
a lot of trial and error.
All right. Hate to say it, Craig, we got to get going. Real interesting stuff. I know there's always so much more to say about every one of these things here, but we'll be back in just a little bit to talk about some more things here in the wireless building. Got to get over and get back to another one. Thanks.
Sure.
We're looking at the Armington Sims engine from the Hartford Electric Light Company. The engine was made here in Providence, and it's coupled up to a Thompson-Houston generator, part of the original Hartford Electric Light Power Company. I think there was 3 of these, if I remember correctly, in a building together. And at some point in time, this engine wound its way up into the foyer of a bank, where it was powered by an electric motor just to show it operating. It was brought here some decades ago, restored to operable condition, and we're here today with Peter, one of our volunteers, and an electrician who has just recently done some electrical work here, and he's going to tell you all about quite what we've done to it.
Okay, so this panel here was actually built by the museum's founder, Bob Merriam, some years ago to recreate what a panel would look like of this vintage, with open knife switches and all kinds of vintage gear that you would find of something of this age. Obviously it's, you know, a recreation, but a pretty accurate one for the time period. Of course, none of this meets any modern electrical code, but, you know, we're a museum, we're about preserving history here. So that's what we have. But recently we modified it to have some new functionality, and what we did was, Randy's going to show you in a second, we have local lamps, and that's what he's going to show you overhead. Artificial load, this is the same, this is just a load bank for the generator. This here gives us the ability to turn off all the lights in the building to demonstrate what we have here. We have a main switch that controls all the input from the generator to the whole panel. We have, of course, being a DC generator requires a field rheostat to control the strength of the magnetic field. Voltmeter, ammeter, indicator light. We've added an AC power connection here, and that's what this does here. This is a transfer switch. The bottom side is AC, top side is DC when we're running the generator on steam. So we have a little safety feature here. This just pulls in a contactor. We have live AC now on our knife switch, and we have lights at 120 volts AC.
And this installation is new in the ridge of the building here, going from end to end. It was formerly just a small panel against the wall, but this has all been recently installed just to make it a bit more dramatic here in the building. And we can light this all up when the generator is running. And with being incandescent bulbs, they will run on AC or DC without any care in the world. Thanks very much, Peter. We'll switch over and get this engine running and see where we go from here. We've got it all hooked up to the lights. So we have a way to hook it up to grid voltage for some lights on the ceiling. You see the connection there that was just made. And now we can go ahead and connect it up to the grid lights. You'll see up overhead here, a line of lights from one end of the building to the other. All right. And go ahead, pull that out. And all right. Now we can connect it up to the generator here. We're going to need a little more power out of the engine. Well, it'll take a little bit of time to build back up. We just gave it a serious load, and it decreased its own field voltage. And it takes a little while to build back up, especially with the load of the lights on it, but it will. Or we just need a little more steam. again for joining us for Steam Up 2020 here at the New England Wireless and Steam Museum. Steam Up is our annual fundraiser for the museum. We would normally have about 900 people here this day, but we're pleased that you can join us via YouTube this year in spite of the viral concerns. We have an immense collection here at the museum, and we hope you can all join us in the near future to see it all yourselves. For today, we're pleased to bring it to you via YouTube. The museum is entirely operated by volunteers and funded by your generous donations. If you can, we hope you can make a donation today using the link in the comment box below or on the museum's homepage at www.newsm.org. The museum homepage is also a great source of information about everything we have here in our collection, including photos and histories of many of the objects. The museum is a 501c3 and your donations are fully tax deductible. I thank you again for joining us and for your generosity. If you'll excuse me just a second, I have a lot more text messages to send. This is going to take forever. Alright, we got to get over to the other building here because I know we're a little late on the Corliss. See what he's got going on. Oh, he's already got it running. Well, I'm sorry we're late, Ernie.
Oh, hey, there you are. No problem.
Looks like you've already got everything running here. Tell us a little bit about it. I know this is the Corliss, but tell us what makes this one so different and it seems dramatically more complicated immediately, but you know.
Well, as anything got added into technology, just think about heating systems for your house, your car, or whatever. The more technology increases for usually efficiency, the more complicated they get. Okay? I believe I mentioned before that steam engines never made it to 10% efficiency. Well, neither did this, but this is the pinnacle of reciprocating steam engine technology and efficiency. Well, really? Yeah, we'll get there in a minute. This engine was so efficient over its competitors when it was originally patented that the Corliss company would give you a factory owner the engine, and you paid for the engine by what you saved in fuel. And guess what? They still hadn't got to 10% efficiency. But, you know,
So this was more than double the efficiency of some of the earlier technologies, but still not even 10%?
not even 10%.
Wow.
Now, when we looked at the New York safety engine, we talked about how slowly the valve moved. Let's real quick hit on steam technology again. What did we do? We heated water in a closed space, right? And we took that steam, which was about 1,700 times expansion, and we piped it to the engine, big pipe coming into the engine. And then we used it as efficiently as we could. However, the valve on that New York safety engine moved very slowly. Look at this.
So yeah, let's take a quick look at everything that we have going on
Ignition
here.
close.
Okay.
Ignition close. What am I doing? What does the steam want to do? It wants to expand, correct? We said that. So, I'm closing the admission valve, I'm capturing the steam in the cylinder of the engine. It's going to expand because this valve pushes the piston that way. And in this engine, it pushes the piston that way almost 4 feet. Huh? Yes, 42-inch stroke on this engine.
Yeah, let me remember now. What are we talking? 16-inch piston on this one, or 20-inch piston? 17-inch piston, 42-inch stroke, and so let's talk a little bit more about exactly. I don't even know what I'm looking at here, Ernie. Let's talk about this a little bit more.
Okay, well let's start up at the governor. Please pan up there. Doesn't that look like something out of a science fiction movie? Well, remember we talked about centrifugal force. As the engine speeds up, that speeds up, and those balls will spread out.
I think I saw that in like a Frankenstein movie or something one time.
That will affect this linkage right here. You can see links. These go to the admission valves.
Oh, I don't know if I'm keeping up with you here.
Okay, this link goes to the admission valve. The admission valve is operated by what's called a wrist plate.
Okay,
So
let me,
it opens.
let me back up here a little bit, Ernie. I gotta get a better perspective on this, because I know this is real important stuff. All right, so you're saying that this here is the wrist plate, this mechanism here.
Okay, well, let's start with that. That's good, Randy, the way you did that. It sounds like you're asking a question. So, remember the eccentric that went back and forth like this?
Sure.
That eccentric is causing this to oscillate and rock.
Okay.
Its official correct term is a wrist plate. That's what George Corliss called it. You can see that this wrist plate is operating the admission valves. They're on the top where the steam is. It's also operating the exhaust valves.
Okay, so 4 separate valves on this engine rather than either 1 or 2 like we've seen before.
So these 2 valves are for this end of the piston or cylinder, and those 2 are for that.
Got it? Okay.
Okay, now, what was George Corliss' claim to fame? Why did he get more efficiency out of his engines? Steam is nothing more than expanded water that was turned into a vapor or a gas. We want to keep it under pressure as long as we can, temperature and pressure and all those laws of physics. So, we open and let steam in, and notice how quickly that closes. Open, close.
Oh, okay, so this over here doesn't actually, the movement of this has nothing to do with the actual movement of the valve. This right here is actually the movement of the valve. Opening right there, let's see. Opening and then closing.
Yes.
That's the valve, rather than, okay, I got you now.
So see how it kind of opens a little bit slowly? That's just typical steam engine. But when you look how quick it closes. What did that do? It trapped steam under pressure in the cylinder. Steam wants to do what? 2 things. Go back to atmospheric pressure and turn into water. So it had a long time to expand in the cylinder.
Okay.
Let's talk about that valve real quick. I don't want to get real carried away on it because we have a whole section on Corliss valves. But look at this. Open, close. Open, close. Open, close.
Oh, so okay, so you have a long, narrow steam port here, and this opens by just rotating a little bit, and then the steam is able to flow through it down the other side.
Exactly. So we open it, let steam in and close it.
I got it.
Let steam in and close it.
Yep, makes sense. So there's one of those in each end of the cylinder. Got it.
Okay. Another thing of efficiency. When you had how many valves on the New York safety engine? 1. That valve does admission, which is hot. It does exhaust, which is cold. This, steam, exhaust. You're never reheating any engine parts. This is always hot. These are always cooler.
So again, let me just take a quick look down here. So these are, down the bottom, we have the exhaust valves. They don't have that same type of trip mechanism on them, but nonetheless, separate exhaust valve here, and then another one down your end over there, opening and closing, and then the actual admission valve up top here, like you were saying. Makes sense? And
All right.
what's the red thing down there?
All right.
I mean,
This-
obviously that's connected somehow. What do we got going on there?
If you look at this, we'll talk about this in a second. It's called a dash pot.
Okay.
The rod goes up and goes here. It's lifted and it closes. When it closes, you hear that little clunk noise. This actually draws a vacuum down here when it's lifted. And vacuum is a space that has lack of atmospheric or air pressure. So what happens? It lifts it up, it wants to go back. It's just making sure that that admission valve that's up above my hand closes as quickly as possible.
Okay.
It just was an added feature to make the engine work more efficiently.
Okay. That's what helps close the valve.
Yes,
Okay.
in a very rapid form.
Gotcha.
Now, one of the things I wanted to point out, as you pointed and looked at the exhaust valves, the admission valves are working quickly. The exhaust valves, they're kind of slow. Some of you may not necessarily agree with this, but if you've ever run a car engine, an internal combustion engine, on an engine dynamometer where you're truly measuring its performance, it is a fact that the opening and closing of the exhaust valve doesn't matter all that much as long as you let the burnt air and fuel out. The intake valve on an internal combustion engine, admission valve on a steam engine, is really critical for performance and or efficiency.
I mean, I don't know about you, I haven't run my car engine on a dynamometer at any point in the recent past, but I guess I'll take your word for it on this one.
Okay.
Let me take a quick look around the engine. We can talk about, obviously this is another one of the valves where the admission valve on the opposite end of the cylinder looks all identical to what we were looking at over there. I see what you're talking about the flyball governor here. See? All right. Now, I know we can kind of demonstrate that. I've seen it done before. So if we were to raise that up, right, what does that actually do? You know what? Actually, let me look up top over here, okay? Oh, all right. I see they're out wider there and narrower there. Okay. Yep. Oh, and you know what? Let me try that one more time. Right? I can see something going on here. Yep. Okay. So that would simulate a lesser load on the engine, correct? If the balls go out, it means that the engine is spinning faster.
And we'll give less steam.
So that would make less steam. Let me go over there and look at that quickly while you move that, and let's see what it actually does. So, hold on just a second. Okay, go ahead, raise that up a little bit.
Raise it up all the way.
All right, sorry, go back down a little. Okay, I can see it pivoting over here. So let's let that do its job. Now, if we raise that up. Oh, wait a minute. Oh, geez, it barely even opens it at all. So I see exactly what it's doing. So by virtue of lifting that up and simulating a higher speed condition, it makes the admission valve open less. I get it. Let me take a quick walk around to see, because this engine is huge compared to everything we've seen so far. And obviously you've got a real complicated mechanism here for the valves, dramatically different from everything else. But let me take a quick walk around and see quite what we have on everything. So of course this is all the steam piping coming in. We've got backside here, a little lubricator to send some oil into the cylinder, and not a lot of space.
If you can pan up here, we have what we jokingly refer to as the T-set. We talked about lubrication on the other engines, and this was another way of lubricating a steam engine by using pressure differences that exist within the engine to forcefully inject oil. This is all nothing more than a cylinder lubricator, which we don't use right now because it's actually in need of restoration. We jokingly refer to it as the T-set, and that was just another way of getting oil into the cylinder, which is under pressure, and the engineer operating the engine didn't have to worry about it as much. He could set it and come by and check it once in a while.
I can't actually see what it says there, but oh, it says, I do see Boston, so that wasn't actually made by Corliss. That was just an add-on piece that he was getting from somebody else.
Just every one of these engines, the lubricators were made by another manufacturer.
I can actually see it right here. Here we have this one, made by Nugent, William W. Nugent and Company. So yeah, totally separate, and that's the same type of thing. We've got a lubricator there, and a very complex extendable rod that's going back and forth to deliver oil from the lubricator down to the wrist pin here in the crosshead, so that nobody had to sit there and move it back and forth.
Okay, even though they tried to make these engines automatic, the engineers still had to lubricate a lot of parts of the engine. There's his oil can, and there was the official place, according to George Corliss, where he stored it.
Nice.
Of course, that would have been all highly polished, because the engineers that spent all day, every day, they treated these things, in some cases, probably better than children.
Nice. This is a unique perspective over here. You don't really get to come over to this side of the engine very much and see the crosshead. And you can really see the stroke, the 42-inch stroke that you were talking about on this one here. And it was very long piston stroke. And of course, because of that long piston stroke, like you were describing, you have a pretty big crank there to accommodate that. Much bigger than what we were seeing earlier.
Remember, horsepower and torque. Torque is a level of push over time. 42-inch push is what's happening here. What's this area of a 17-inch piston in square inches? I don't know. I don't do that level of math in my head. This engine probably ran on 150 psi times that, and we did just figure out a little while ago, this engine has 27,000 foot-pounds of torque.
Wow.
And 150 horsepower.
I'll have to do that math a little later on because I also can't do 17 or 7, you know, 8.5 squared times pi, but times 150. But that is interesting. Yeah, you get that, you know, thousands of pounds of pressure over the course of 42 inches of stroke.
Also, that torque was available instantaneously. As soon as the engine started to move, it moved every piece of machinery in the factory in most cases. So that's instant torque.
Yeah, you have 100% torque at 0 RPM. Unlike electric motors or particularly unlike gas engines.
Well, remember, the electric motors are close, but not at zero. It's as soon as the electric motor starts to turn. Anyway, once again, Randy is almost standing on what looks like a carpet runner. That's a drive belt. It ran a whole mill off the outer diameter of the flywheel.
That is one big belt, I can tell you that. You know, I also noticed here, Ernie, some of the all the work, you know, that wrist plate that you were describing earlier, the castings, everything that's here has a certain level of artistry to it, you know, just a fit and finish. It's not just a big square block of metal, because obviously that would have done the same thing, but they really tried to put some care into everything that they were doing and make it look pretty.
Well, Randy, way back when, this engine was built in the late 1890s, and I'm not saying people don't take pride in their work anymore, but the work is different. If you're writing software, programming software, designing electronics, your engineering expertise is not that visible. It's the final product that somebody gets to use and may never even see what you truly designed. These engineers and designers way back then, they designed this and it worked, but also their stuff was so visual, and they made it basically, like you said, artwork. They were proud of what they did, and I am not saying that engineers and designers are not proud of what they do in our world, but it's a different world. You know, when was the last time most of you ever saw the actual software that makes this video happen? And even if I did see it, it wouldn't mean anything to me.
Yeah, sure.
But this, there's the product of some designer slash engineer or engineers, and everything they did, they took it as art.
Nice. That is one big flywheel, and I'm getting some serious breeze coming off of that thing, just turning at its relatively low RPM as it is.
RPM. This engine's running at about 25 RPM, maybe it's running at probably less than 50. This engine only ran at 80 or 90 RPM. Huh? Well, just think of the inertia. Remember, as you spin something, it wants to leave due to centrifugal force. Can you imagine the inertia that's in this flywheel even at 80 RPM.
What are you thinking on this one? I know we talked about 7 or 8 tons on one of the other ones. What are we thinking here?
This flywheel is 15.5 feet, and from what we did on the other one, I'd say you're looking at 8,000 to 9,000 pounds at least, if not 10,000 for each half.
Yeah, an easy 10,000 pounds per half.
And you can see the flywheel is in half.
Yep, two pieces that are bolted together here in the middle. That allowed it to be built and transported to where it had to go, and then assembled around the crankshaft, of course, because you wouldn't be able to... Oh, there goes a bolt. It's moving way too fast. I can't actually see it over here.
There you get a chance.
But you had to be able to put it together around the crankshaft in the middle, and that was how they achieved it, is by making it either multiple pieces, in this case just 2, and then bolting it together on site. All right, let me just keep looking around the other side here. Much bigger than anything we've looked at so far, but fascinating to see that it's got all of the same parts. You know, a little more complicated with the valve, of course, but otherwise, you know, it's got a big wheel, it's got a crankshaft, it's got a piston, connecting rod.
You said much more complicated, and you took the words right out of my mouth. I was going to say much more complex, but it's all in the Corliss valve here. That's where the efficiency came from.
Oof. Feel that breeze again over here. Let me take a look, because that pit goes down quite a ways. That diameter of that flywheel. Now, I've always thought we could turn this into a giant slip and slide. I really want to, you know, put a little slip and slide down the other side of this thing and just go for a ride, but, you know, it doesn't actually seem like a great idea.
No.
Maybe not,
I
huh?
think we would have parts.
Ah, damn. Of me? Parts of me?
Let's not discuss that.
All right. All right, very neat, Ernie. This is much more complicated. I'm glad we really got to take a good look at it. Definitely operates a little differently from the other engines.
Let's just recap this really quickly. First off, we started with steam engines. We talked about manufacturing in Providence, Rhode Island. George H. Corliss Manufacturing Company was in Providence, Rhode Island. Okay? George Corliss perfected the Corliss valve here. And that really is the claim to fame on this engine. The rest of this engine, just like Randy just said, it's got flywheel, it's got a crankshaft, it's got a piston rod, it's got a connecting rod, it's got a crosshead, it's got an eccentric operating this. The eccentric really doesn't operate the valves. This operates the valves, yes, through the eccentric. But the key point is closing it almost instantaneously to save or capture as much pressure in the cylinder as possible.
Got it.
Thank
So
you, George Corliss.
that's really the big difference. It's all about the valves. Got it. All right. Thank you, Ernie.
Thank you.
I think we'll be back again. We got to really look at this one again because it's so much to take in. I know we'll be back a little bit later. Thanks. All right. So what we've got going on over here is a demonstration of the principles I talked about a little earlier with the Newcomen engine. Got a little steam going on. I'll get out of the way. So I had said earlier that the Newcomen engine relied on negative pressure within the cylinder to actually exert force and pull it down. And I can only imagine that people have a hard time relating to that, understanding what sort of negative pressure would be. Well, in the air all around us, in the atmosphere, we don't feel it, but we've got about 14 psi of pressure on us at all times. It's called standard pressure at sea level. And Newcomen didn't understand what he was doing, but found something that worked. He took advantage of displacing all of the air with steam, sealing that chamber off, and then putting a water spray into it to make all of that steam condense, drawing a negative pressure inside of the cylinder and letting air pressure push that piston down. I had heard in some cases that he started off with maybe a 20-inch piston, and I think one of our other volunteers here had said that some of the larger Newcomen engines had 50-inch pistons in them. So you do a little math, 25 squared times 10 or 14 psi times pi. You get a tremendous amount of pressure on just that flat disc from the atmosphere. So, taking some idea of what's going on here, we're filling, what I have is a little burner underneath. We can, let me take a quick look down there. We've put a little bit of water in the bottom of this barrel here, and just have a propane burner going underneath there. Nothing real special. Just heating up that water and letting it turn into steam. Now, because of the way that steam expands, you get a 1,500 times expansion. I think Ernie might have said earlier 1,700. Sometimes it's a massive expansion of volume between water and steam. So this amount of water right here, probably even less than this amount of water right here, will completely fill this barrel with steam and displace all of the air that's in the barrel. We've been steaming this up for just a couple minutes here. It's well full of steam. I don't really feel like touching that to any great extent right now, but we got to seal this up. And the whole idea is let that keep going, Mike. See if that'll keep going just a little bit, or if it's going out. Oh, we're gonna just relight it here because I was going to go for just another second. You can see how quickly that steam dissipates because we have almost zero water in the bottom of the barrel here. Looks great. So I did a little math earlier, and I was thinking that going back to what we were saying about the Newcomen piston size and so forth, the outside of this barrel, between the circumference of it and the heads, has about 3,300 square inches of space to it. If we imagine that we're going to draw even 10 psi of negative pressure here, probably not quite the whole 14 pounds of atmospheric pressure, but if we get 10 psi of pressure on the outside of this barrel from what we're about to do, that'll mean 33,000 pounds of pressure trying to crush this barrel in. And you'll see just how powerful that concept of the Newcomen engine is. So, we're ready to go. Got a good amount of steam coming out here. What I'm going to do, I'm going to put the lid in here, just cap this off to seal up what we have going on inside. We've killed the power. I didn't happen to bring my drum wrench with me today, so we're cheating a little bit. Let's see what happens. I know we've got to give it a little bit of time. You can already see the head of the drum starting to pull in. And if we just hit the outside of the barrel with a quick spray of water, it'll help to condense a lot similarly to what Newcomen was actually doing. Once it goes, it just wants to keep on going. That's an awful lot of negative pressure right there.
I don't know how many men it would have taken to stand on that barrel and try to crush it down, but an awful lot more than what we have around here. So there you have it, the power. Unbelievable, it just wants to keep on going. The power that Newcomen was harnessing in his engine, the negative atmospheric pressure. I don't know what I'm going to do with that barrel now, but probably not much. That's, you know, I don't think it's going to work. Everybody wants to say we'll just boil the water back again and try to blow it up, but I really don't think it's going to work out quite right. All right, really cool experiment. I'm glad we were finally able to do it here.
I hope you're having a great time today viewing our 2020 version of Steam up here at the New England Wireless and Steam Museum. We're happy we can present this look into the museum's collection here on YouTube, as the museum is currently closed due to the coronavirus concerns. I'd like to take a moment to talk about the educational value of everything we're doing here at the museum today. As technology continues to evolve and today's youth is being engaged by whatever the latest and greatest technology is, fewer and fewer of them get any exposure at all to the fundamentals of how things really work. Just last week, I was shocked to speak to a high school student who had no comprehension of what a lever was. We here at the New England Wireless and Steam Museum see an increasing need for small, independent organizations such as ourselves to fill in the gaps of knowledge that aren't being taught in schools today. Arguably, I think we have the greatest technology here. It serves as the fundamentals for everything we enjoy today and the building blocks for what kids will do with their tomorrow. Many of you may have heard of the STEM or STEAM initiatives taking place in education today. It stands for Science, Technology, Engineering, Arts, and Mathematics, and is a renewed appreciation for how important these things really are in education. We think the New England Wireless and Steam Museum is a great resource and can help educators today complement their efforts. As such, building out a robust educational program here at the museum is an area of specific focus. We have numerous educators amongst our volunteers here at the museum, but of course, their efforts also require funding for the sake of materials and modern technology to deliver our lessons and messages to visiting students. We hope you'll support their efforts in everything we do here at the museum by making a tax-deductible donation today. You can find a link in the video description below or on the museum's website at www.newsm.org. One quick note, for anyone with an IRA and a required minimum distribution, or RMD, the tax law was changed just a couple years ago. Your donation to the museum today can count toward your RMD and be tax-free. That means your donation goes 20 to 25% further with us than it would otherwise. I hope you'll consider a small donation today to keep all of this alive for generations to come. Thank you.
So this is a mechanical television. It works exactly the same way as what we used to consider to be a modern CRT-based television, which has been superseded by all the flat screens you have in your house. Probably nobody has a glass CRT in their house anymore. But believe it or not, this spinning disc was actually a television, and if we did some modifications to it, you could watch MTV on it. This was originally generated...
You know, Mike, I gotta interrupt you. MTV, come on, we're really showing our age here.
The original concept of this came from a gentleman in Germany named Nipkow in 1884. So most people think television is 1940s or maybe 1950s technology, but it's been around for nearly 150 years now. we did a little demonstration earlier. I can light up the back of this with my phone just so that we can get some light on it. And this will give you an idea of the viewing area. You can see the lights on this, and if we spin this, you can see the scan lines running across this, just like what we consider to be a modern glass CRT would do. We've also got another one that's here that was made by a company in Boston. It has the same effect, but instead of having a disc on it, it's using a drum. The advantage of the disc, the drum versus the disc, is that obviously over this small area here, there'll be a little bit of an arc as the hole passes by. This has holes on the outside of the drum here. And since it's traveling by like this, there won't be an arc on it, so you won't get the slight bending effect on it. So this, you can see a hole right here and another hole right here. So this drum would spin and give you the raster on this. And since this, again, has such a small viewing area on it, it's got a magnifier out on the front of it to increase the size of the picture on it. This is the AM radio receiver that went with this, and this was sold as a set for about $40, which is maybe $600 or so in current money. So they weren't hideously expensive. You needed 2 AM receivers to work with this. One of these would be the audio side of this, and that went over a commercial radio station. In the Boston area, they were using WEEI and WBZ for the audio side of it, and then they had experimental radio stations, 500-watt experimental stations, that would broadcast the video side. So you needed 2 receivers. So this is the AM receiver that was part of this kit, and you would tune it to about the 1.2 megahertz range for the video frequency on it. It's got a headphone jack in the front of it so that you could plug your headphones into it and then tune the frequency on it for maximum signal on it. When you unplug the headphones, there's a cable right here that runs over to a neon bulb that's just inside here, and the RF signal that you're getting from the TV station would control the brightness of the neon bulb that's inside of this. You'd also get a pulse out of this once per frame, because as this disc is spinning in here, the beginning point of the frame on here has to be synchronized with the signal that you're getting from the television station. So there's a circuit that's in the back here that will pick up that pulse and then slightly vary the RPMs of this to synchronize this. So you would turn the motor on, and there's a speed adjustment over here that would control how fast the motor is spinning. And you would be looking inside and seeing pretty much trash on there, and you would slowly reduce the speed on it until you got close to the right RPMs for this, and then the circuit that's in the back would take over and synchronize the image on that, so you'd actually get to see a TV image on this.
Very cool stuff. All sounds really good. Something that most people have never seen. Mechanical television, who would have thought? Thank you, Mike.
Okay. There we go. Now we've got WHIM for a little country music here. This is a Freed Iceman NR5 radio. It's obviously of the period that it's got vacuum tubes inside of it and a Nutridyne type receiver. One of our relatively clever volunteers put FETs on the bottom of the vacuum tube sockets on this. Vacuum tubes and FETs are both voltage-controlled devices, so they work pretty much the same way. So he put FETs on the bottom of the vacuum tubes on this, so we can power this from a 9-volt battery, and all of the circuitry that's inside of this is still working exactly the same way as it did with the vacuum tubes on it. It's just got FETs on the bottom of it. And as you can hear, we're picking up one of the local country stations on it.
Something that's actually real intriguing to see the whole thing powered by a 9-volt battery, you know, in lieu of the vacuum tubes that are so power hungry. Neat stuff. Let's head into the maze building now, where I know we've got Tim Straw waiting for us with some models. The maze building is seeing a little bit of renovation these days, so unfortunately things are a little disrupted. But thank you for accommodating this, Tim. I know this isn't the usual environment outside and so forth, but happy to get this thing done. The museum has 50, 60 models. I mean, we have quite a number of...
Probably 100.
Oh boy, you know, small engine models in the collection here, and you know, love to get different ones out for people to see from time to time. Appreciate you showing some of us here.
Okay. So this is the model of the engine from Little Juliana, circa 1808, built by John Stevens, Stevens Institute of Technology fame. And it's rather unique. It's a single cylinder driving twin counter-rotating shafts. And the large iron gears are what keep things synchronized. And being a marine engine, it's necessarily reversing. So by shutting it down and changing the gear ratio, or the gear angle, and starting it up, it should start running in the opposite direction. There we go.
Let me just go around and take a look at the valve on that, because that's a pretty unique valve set up there too, Tim, huh?
Yes.
Very interesting. So the two big gears act both to synchronize the shafts, keep that piston straight, and as flywheels.
This model was built by Ray Hasbrook, a well-known machinist and model maker.
That's very, very neat. Very unique mechanism for sure.
Thank you. This little guy is a horizontal single acting, so the steam or air is only pushing on one side. But it's interesting, it's got a rotary valve and it has a rotary reverse, so you can change the direction.
Oh wow.
It runs a little faster in that direction. Slow down and it's going to go that way.
Incredible to be able to build things so small that still operate just exactly the same way that the larger ones do.
And right now we're running on about 14 pounds of air, which is plenty for these small models.
Yep.
This is a trunnion engine, kind of unique in that it has a cylinder that's below the crankshaft. And these are quite often used in paddle wheel boats. Obviously you can see where the shafts get extended out to the side wheel paddles. And there's a little valve in there. I spent a fair amount of time restoring this, replacing missing parts, and then discovered that it was never intended to run. The valve ports are too small. They're 1% the area of the cylinder head,
Yeah.
the piston, so you just can't get enough air in there.
looks beautiful. I mean, the amount of detail that somebody put into this is absolutely amazing, but unfortunately, it might have been just made to look pretty and never actually intended on running.
I think so.
Oh well, still looks fantastic.
This is a nation, it's called a bottle engine. You can probably guess why. The frame is shaped like a bottle with cutaways. And it was a very common type of engine, single cylinder, double acting. You saw in the other videos how the slide valve, the steam chest, the D valve sliding back and forth to admit air from the bottom or the top.
Yeah. So let's see. This is going to be the steam or air in over here.
Yes.
And that's the exhaust right there.
Yes.
Interesting. I don't remember seeing this one run in years past, but no reason that we couldn't just hook that up and try it at some point in time, I'm sure.
You could probably get it running. It feels pretty smooth. Just a couple other examples of model engines, steam engines. During the show, people asked me, well, what are these for? And what do they do? And I said, they're for entertainment. We get, some of us get pleasure, and miniature machinists, designing and building these, and then get more pleasure when they actually run.
Sure. And I suppose, you know, back when this was an emerging technology, everybody was so fascinated by it. You know, they wanted to capture it themselves and see if they could achieve the same thing that these big engine manufacturers were, and you know, as a hobby, just doing it in miniature.
And that's a good point. Over 100 years ago, these type of toys were very popular. You have a little burner, typically an alcohol burner, and a simple firebox, and then a boiler, a sight glass for the water, see how high the water was.
Yeah.
And then this is a little single piston steam engine. And this pipe coming out the top is the steam source. And it would move back and forth. And on a happy day, you'd get this thing running on steam.
Yeah. I've certainly heard of the Whedon models before. So that's completely functional.
Yes. And it has a little excitement. It has a whistle.
Very interesting. Yeah, so this was, I mean, never mind enthusiasts making for it for themselves, like this was such a popular technology and stuff in its day when it was emerging that this was a toy. This was a children's toy, or, you know,
Yes.
you could buy it and play with it. You know, imagine, doesn't seem real fitting today. Like you don't see Johnny at home playing with his model steam engine and boiler these days.
Especially with real fire.
I suppose not.
They also made this kind of engine with plug-in-the-wall electric heater,
Right.
which maybe was a little safer.
A little safer. You still, of course, had the pressure vessel of the boiler itself, but at least there's no fire.
Yes.
Hopefully. Hopefully no fire in your house.
Right. Okay, this is this model of the engine that was on the USS Princeton, the first U.S. Navy warship to be screw-propelled instead of side-wheel propelled. Gave them a big advantage in protecting propulsion during gun battles. And this is a rather unique design. These are semi-cylinders, so you don't have a round piston moving back and forth. There's a panel or a board moving back and forth. Sometimes this is called the barn door engine. You'll see this is the pistons driving the valve, the barn door back and forth. And two cylinders are kept synchronized by eccentrics on the shaft. From the back side, you get a better view of the
Sorry.
levers.
Sorry, you know, there we go.
The levers that operate this. It looks kind of wacky. The purpose of this engine was to keep the profile down below the water line.
Oh, so, you know, get it as deep in the boat as possible, but still have it not very tall.
So if a cannonball came crashing through the hull, it would skim across the top, but not take out the engine and the propulsion.
Huh. It's certainly a unique design.
Yes.
I can't imagine that they made too many of these.
No,
Might have been the only one.
it did lead to the same person that designed this did the engine for the USS Monitor.
Oh, okay.
It was a low profile that had conventional pistons and cylinders.
Okay. Very interesting.
Maybe I'll let you describe this.
Well, this one here, I gotta say, don't know a real lot about it, other than it being a beam engine, of course, a single-cylinder beam engine. This was down in the basement here at the museum, buried under some boxes just a couple years ago, and managed to see it one day while trying to shuffle things around. And part of the valve linkage here was damaged, so I just had to make a quick repair on that. And other than that, it runs great. I'm always fascinated by the parallel link motion here. Something that James Watt had to develop when he made his modifications to the Newcomen engine, just to keep that piston rod vertical at all times, so that well, maybe we can slow it down and take a little closer look at it. But you know, that kind of complicated system of levers right there and rods is what helps hold that. There we go, beautiful. Helps keep that piston rod vertical at all times. Real simple when you actually get right down to it, what it actually does. But God, it runs beautifully even at such a low speed.
The other feature here is this flyball governor that's connected through this gearing.
Yep.
To a shaft which goes to the input valve. So it's controlling or maintaining constant speed in the engine.
Yep. Very interesting to have that go through here. This linkage here with the little bell crank and presumably a counterweight to kind of balance the entire mechanism. This would balance the valve, and then of course this inside is the typical slide valve inside of there with that cylinder. Now I know there's a little confusion on the orientation of cylinders, because between the Newcomen and Watt engines, this is the standard orientation with the piston rod facing up, and they call the ones facing down inverted. And somehow or another, that's always seemed a little backwards in my mind until you get right down to where the reference, or where the point of reference is. This was the original and the kind of the standard configuration, and then the inverted being the other way.
Like this one.
Yep, this right here would be an inverted steam engine. Very cool. Well, thank you, Tim. These look great.
Right.
We've got a lot more to see, both today and, of course, with the models in general, and hope everybody can come out, see them in person here, maybe next year when we're up and running.
I'm looking forward to it.
Great, thank you.
So enter the spark. I mean, after the transatlantic cable was successfully laid and we had communication worldwide, people like Heinrich Hertz were experimenting with sparks. And just like static electricity or lightning, sparks became a very important step into wireless radio. And a spark is, I mean, we're familiar with sparks, but sparks disturb the atmosphere. I have just a quick demonstration here to show you how. This is just an AM radio tuned in between stations, but this is a transmitter. It's a 9-volt battery, a file, and I'm making a short circuit technically, but it gives static on the AM radio. And that is literally a transmitter transmitting a few feet. So if you picture adding more power, adding an antenna, making things bigger and bigger, making the spark bigger, you can start to transmit a staticky sound like that for miles, and eventually hundreds of miles. So what was discovered is that if you create a spark between, these are all gaps. If you can get a spark to jump that gap, it disturbs the atmosphere enough to where if you have a method of detecting that spark, you can start to communicate wirelessly. So there's a nice example in here. These fins, you see these aluminum fins on each side. If you can get a spark to jump the gap on that device there, and then there's no wires attached, these fins will pick up the energy in the air, and with batteries connected, can actually ring that bell by the coherer, which detects the spark and completes the circuit.
So with the sparks, Craig, what were they doing? I mean, same type of thing. So they employed the Morse code.
Right. So now you can take
The same code that they already had, apply it to sparks, and you could transmit that over distance wirelessly.
Right. So you can make a spark when you wanted to with a key across the gap, and have a receiver hear the message across with no wires. So after all that laying of the cable and everything else, now we're working on the next revolutionary part of radio, wireless communication. This was still with Morse code, still considered telegraphy. Voice comes soon after, when we learned how to, or discovered how to take the human voice and convert it into electrical impulse and add it to a radio wave, and then you can start transmitting with voice, and then you get music and AM radio and speech, and it evolves and as to be radio, which is a radio like this is so common today we don't think about it anymore. It all started with the telegraph and cables, and then spark for wireless.
Interesting. All right. We're a little short on time. We're talking about sparks. I know, the little sparks on the battery over here, nothing real impressive. On your file, nothing real impressive. Why don't we head over to the other side, because we have something a little more impressive in the way of sparks. You can see quite what that's all about. I'll follow you.
So right here is obviously a high voltage rotary spark gap device, and the rotary spark gap, it spins, and the sparks occur between these posts here and the spinning wheel, and that did a couple things. It kept the elements cool, but it also added more of a pitch to the sound of the Morse code, so it wasn't just such a raw sound. It was more almost musical, not quite as musical as it is today, but it gave it a tone which is much more pleasant to hear. Not that it was any softer, but we can demonstrate this.
Yeah, let's take that off for just a second. Let's see it spinning.
Right.
It's actually going much faster than I would have expected it to go. Good that we watched it there.
And off to the side we have a Morse code key. You'll see why we keep it off to the side. But if you watch between here and here, ready?
Sure.
Now that does a lot of atmospheric disturbance. This is not hooked up to an antenna. If it were, it would go many miles. But
so now, just like I was with Mike a little earlier. He's right behind you. We're going to do a little something with the fluorescent bulb. We may as well do it.
Oh yeah.
Some people might have seen the short video that we did a few days ago with the fluorescent light bulb here. We'll kill the lights here and try this again. We've got the spark gap transmitter here hooked up to a Tesla coil, so that's trying to dissipate that energy out into the atmosphere. And we'll try it here. Yep. Get a little closer.
Now, Mike, if you get your hand a little closer up that bulb, you'll see that it stops right where your hand is. Very cool stuff. All right. Cool. That is some high power.
That sure is.
I can understand why they would need to keep those tips cool with the amount of power flowing through the gap.
Right.
All right, let's head back over the other side. I know we're going to talk about one of the inventors here, Fessenden at least, for a little bit. There's no end to the equipment here at the museum, the stuff that can be seen. I wish we had more time to talk about every little bit and piece here, but people are going to have to come and see it for themselves. Absolutely endless. First step. I wasn't even thinking about this one. First step in the Fessenden discussion.
This is a little bit of commercial application of Fessenden's experimental work on it. This is a fathometer, so this measures the distance from your ship to the bottom of the ocean. And this was developed by Submarine Signal Company, which is just north of Boston, and developed by Fessenden. My understanding is that this was a little bit of an accident, that he was hired by the U.S. Navy and given a small ship called the Isleman to make a iceberg detector. And he was, at the time, doing a lot of work with communicating underwater to submarines by sending acoustic waves through the water. So he was using the same transducers to send a wave horizontally through the water to see if they could get a reflection back from an iceberg. What he noticed was that there was also a reflection coming quite a bit later than the reflection from the iceberg, and finally figured out that it was coming off the bottom of the ocean, and decided to turn it into a commercial product.
Interesting. So radio waves, who would have thought a fathometer, depth finder, and so forth, it's nothing more than a radio wave being bounced off, or sound wave being bounced off the bottom of the ocean, coming back. Any idea on the time period on that, Mike?
Actually, I don't. I'd say 1920s, maybe.
Okay, interesting.
Actually, we can look in the diorama there, and there's probably a date on the ship picture.
More information. Great. Let's see it again. Endless amounts of equipment here. So forth. There's a few things in transition in the boxes here as we try to shuffle a few things around this year. But not only have we talked about technology here at the museum, but the inventors of the technology themselves. And Mike, I know you're expert in Reginald Fessenden, so here we are, one of the inventors of some of the radio technology.
Yeah, Fessenden worked out of Brant Rock, which is part of Marshfield. It's about 30 miles south of Boston. He also worked out of Virginia for some of his tests, and he had another station in Scotland, and he was at the same time as Marconi was trying to do communications across the Atlantic. This particular antenna and station here is in Marshfield, the town that I grew up in. So I was always a fan of Fessenden because he was considered one of our local guys. And while Massie and some of the others were doing telegraphy through the wireless, Fessenden was actually doing voice using a rotary spark gap transmitter like the one that you saw demonstrated just a few minutes ago. The receivers were the same as what you would have for radio telegraphy. So what Massie was doing, you could use one of Massie's receivers, but with the voice broadcast on it. He did the first voice broadcast in Christmas 1906, and played his violin, recited poetry, a bunch of things. And I imagine some of the people that were shipboard that were expecting to hear radio telegraphy and hearing somebody's voice and a violin playing were more than a little bit surprised that technology actually existed.
Neat. I know there's a little controversy behind that, whether that actually happened or not, but what was it? Massie claims, I'm sorry, not Massie. Marconi claims that he was the first to do it,
Yeah.
but it was what, 6 or 7, even 8 years later or something that.
Yep.
Interesting. One of the lesser known names, I guess, in the industry. All right, excellent. I know we've got a little bit more of the stuff on Fessenden that you've done here yourself at the museum, a little background information. Don't have a lot of time to talk about it today, but as per everything else, so much more to see. I see it there about the station at Brant Rock. Love to get to it, but we'll have to do it another time. Thanks again, Mike. No end to the equipment here at the museum, the stuff that can be seen. I wish we had more time to talk about every little bit and piece here, but people are going to have to come and see it for themselves. Absolutely endless. You know, this entire wall arranged by a manufacturer back in the day of equipment. So many manufacturers were trying to do basically the same things and kind of an evolution of things, but you know, a lot of people trying to, or a lot of manufacturers all trying to do the same thing in different formats. So
while we're at the museum, a lot of people take a look at all this radio equipment that dates back to 1920 and before. But very often, this device right here is ignored because nobody knows what it is. So, any guesses? It looks pretty streamlined.
An eggplant, a very oddly shaped eggplant.
As a shaft, that turns, wires, and being what looks like aerodynamic. That's a big clue. So.
The first supersonic, backwards flying something or other.
Close. Let's take it outside and I'll demonstrate. I'll show you what it's all about.
All right.
So this device is, this one fascinates me. This is an aircraft wing-mounted radio spark gap generator, and it provides power for spark gap communication from air to ground, and in this particular case, air to ground only. So we're going to pretend this is the wing of a plane, and it can be wing-mounted, or eventually they mounted them on the landing gear to keep them out of the way. So what happens here is we need a propeller to turn this shaft, and the airspeed of the airplane would turn the generator, provide spark power inside for our communication, except we have no propeller.
So why is this a separate piece, Craig? I mean, why can't they get power? Do they have some sort of other source of power? Or?
Well, we need high voltage for we need the rotary spark gap, which is inside, built in.
Oh, you know what I'm thinking too?
To provide
with the evolution of technology, this being an evolutionary piece of technology, rather than rebuild the plane, they just stick this on the planes that they already had. Makes a lot of sense.
And we're talking about a very narrow slice of history here, because this became obsolete very quickly because it was not efficient. You had to drive the plane, fly the plane very fast, top speed to make this thing work. So nothing up my sleeve, but we do have a propeller. So the way this would work is, and now you can get a better understanding of what's happening here. If this were mounted on the wing, plane's flying fast, 100 miles an hour, maybe 125. Could be a single engine reconnaissance plane, and the wind speed itself would rotate this generator and power up the spark gap, rotary spark gap inside, and give the pilot or co-pilot, depending on how many seats the plane had, the power necessary to communicate to the ground. So he could be doing a reconnaissance mission, and of course you need a Morse code key, so very often they would wear the key on their knee while they're flying and send Morse code to the ground. Except one thing's missing also. You need an antenna. So it gets really cumbersome, but on the side wall of the inside of the plane you have a wire reel of perhaps 300 feet of wire, and this would be paid out and let trail behind the plane. So now you have a plane flying top speed, 300 feet of wire as an antenna trailing behind it. This generator spinning, providing power for the pilot or co-pilot to send Morse code to the ground.
So potentially one man, one pilot reconnaissance plane, he's flying his, biplane, whatever it happens to be at the time, right? this person, he's worried about flying the plane, keeping the plane in the air, doing recon. He's got to deploy the antenna, be sure that he's going fast enough to spin the generator at the right speed to get enough power out of it to do what he needs to do.
To send important information.
Keep looking at what he's trying to do recon on, worry about all these things. He's got the antenna deployed, keep flying the plane and send his message.
And before he lands, that's the point.
Spool up the antenna before he lands.
Bring the antenna in.
Oh my gosh. I can understand why this might have failed in a,
Well, keep in mind that for a while, there's this small time period, and I'm thinking less than a year, because it became obsolete very fast. But this was transmit only. This is not a receiver. So in order to get receipt of the transmission, the pilot would have to look out the window to the ground crew, and they would have to signal somehow that they got the message. So they would lay out white strips of material with lead weights in the end of them to keep them down in Morse code, which sounds really impractical and taking a lot of time. Or they would actually make letters with it, but short things like K for, okay, or anything that would affirm that they could receive the message.
Even like some of the code that you said that you were talking about in the other building for the Morse code, just abbreviations for things that they had, standard code.
And but sometimes they needed to send a message up, not just received. So they made what's called a poppet box, and it's basically a 15-inch by 15-inch square box that's black with a lever, and when you pull the lever, it exposes a white panel, so they could go back and forth with this lever and actually send Morse code back up to the plane, because the planes weren't at first equipped with receivers. So now picture all that. You're flying the plane full speed, circling around after you sent your message, and reading Morse code from this poppet box to see what the message is from the ground. Soon after that, Marconi installed receivers, transmitters and receivers in aircraft, and of course, in time, it became commonplace.
Well, they were trying to get that technology in place as quickly as they could, so the technology is still evolving. They got it up into the plane, they started this communication, and then it got outsourced or outpaced. The evolution of technology took over. They had to just replace it all very quickly.
Right.
Interesting. That's an awful lot of work to be doing to fly the plane.
So hopefully we'll get this on display with the propeller, and it'll make a lot more sense when you see it.
And I suppose if they're doing recon in some sort of, God knows, enemy territory or something like that, they're trying to do all this while attempting to not be shot down.
Right.
Ugh.
Right.
Hold on, let me look at the ground to receive the message. Is there something going on down there on the ground? I gotta look and see what it is that's going on while I try to fly the plane and avoid the enemies in the air.
I'll send you the video clips of us doing that.
The sounds crazy.
Yeah.
Very interesting. Thank you, Greg.
It's a great piece. Thanks.
Let's head back over into the steam building to look at a very unique engine here. It's time to take a look at the Colt-Baxter. It's a very unique engine here at the museum. It's more than an engine. You can see it's we see the this large casing on the bottom, this large cylinder with a relatively small upper section here, and small, thin, spindly connecting rod and crankshaft up there and so forth. Relatively small flywheels. The scale, what throws everything off here, and the thing to note that makes this engine unique is that the bottom is a boiler. It's a self-contained packaged boiler unit. You've got the boiler in the base, and the engine cylinder is actually embedded in the boiler so as to minimize thermal losses, by eliminating all the piping and the insulation necessary on the outside of that cylinder. It eliminates the thermal losses that would normally have to be dealt with there. So somebody could buy one of these and wheel it into their machine shop or woodworking shop, maybe even a laundry or something like that, and basically connect up a chimney to it, light a fire underneath it, and be off and running with power taken off of one of the pulleys there. So this engine is missing, or the boiler, should I say, is missing its outer shell. You see down the base here, this space. The firebox is actually right here, around the other side. Fire would be lit in there, and there's an internal passage that would make the flame and smoke go up inside of the interior here, and then back down again, out this little passageway right here, and then up inside of an exterior casing that, you know, basically encompassed this before it made its way out to a chimney. That covering is gone, and I can only imagine it would have been incredibly difficult to get a draft going in such a situation where you've got that incredible up and down of the way that the flue gases have to travel. So let's get her going. We've just recently added this flyball governor here. It's not actually connected to the steam supply at all, but it does provide us with a very interesting look into the action, because we've overdriven it. It was something that just happened to fit on here. We've overdriven it with the belt and pulley configuration here. Before I really get onto operation, I suppose I should say this was built, it's called a Colt-Baxter, built by the Colt Firearms Company around 1869. You see, at the end of the Civil War, Colt Firearms, of course, famous for their contributions there and firearms during the Civil War. The demand for guns dried up very quickly, so they needed to find something else that they could make. This was what they turned to, and they managed to make 300,000 of these in 3 or 4 different sizes between, say, 1867 or 66 and about 20 years later. This was passé because Edison had invented the electric motor by that time, by the mid-1880s, and things were starting to, a small shop owner could install an electric motor instead of having to put one of these in place. But as with everything of the time, you see kind of the intricacy of the casting there. Those finials up at the top on the corners, it's a little high to reach up there, but the finials here are actually the oil cups for the crankshaft. Let's get her going and see what it looks like. So like I say, we're overdriving the governor here. Makes it great for demonstration purposes, but it means we need to drive the engine very, very slowly. Again, is also great for demonstration. So this engine is very quiet. The noise that you hear is actually the governor doing what it should, in effect. You see the fly balls there. I'm going to slow this down quite a bit. Let's see, maybe a touch more here. And you can see the stem at the top, lowering there, raising up again, lowering. And that's with the change in speed. That's the actual valve stem and how you would adjust the speed of the engine. You know, the valve stem reacting to the change in speed and the movement of those fly balls coming in and out. So that's the mechanical part of what a governor does in action. But let's look at the engine a bit further here. Obviously we're running it incredibly slowly, but it would run quite a bit faster than this. On this engine, the vertical design, we've got the piston rod here, of course, connected to the crosshead, connecting rod, and then next to it, the small rod here would be the valve shaft running off of the eccentric up top. Just like any other engine, at valve eccentric, you know, with this connecting rod there down to the valve that is inside of the cylinder, just like the piston here. So a very unique design, boiler or engine within the boiler, built by the Colt Firearms Company right in Connecticut. Let's take a look over at the Granger engine, another very unique engine here at the museum. Let's kill this, turn that off, and take a quick walk over here. And see the Granger. Now I've spent a little bit of time, I've had this pre-warming here. We can see the steam coming out of one of the drains here. A little condensation coming out of the other. Let me just spin it over a little bit. Also made in Providence, like so many things around here. There we go. Should be pretty free. Now, of course, what we have to do, you can actually still see a fair amount of condensation coming out there. What we can do, close these off most of the way. See the steam coming out down here. Let's close these valves off most of the way. Real simple, similar to what Ernie went through to start the New York safety engine. Of course, this engine is so small that we can just turn it over by hand to get the valve action going. So give it a little bit more flow. Simply give it a spin. Maybe a little bit more. No, not quite. There we are. You can see this very unique inclined cylinder design, and lots of different manufacturers were trying different things to not only come up with novel designs, but also to accommodate varying needs. I'm not really sure quite what this one would have been about. Maybe just as a means of draining the cylinders more effectively. Also very well might have been to fit in a unique space. So, as with some of the models that we saw, and other unique cases, say a paddle wheel steamer, the steam engine that would be in a side wheel paddle wheel steamer boat would be dramatically different from something that was put in a factory like some of the other engines here, just because it needed to fit within a certain geometric configuration. Similarly, stern propeller engines were very different. Well, that might have been the story on this engine here. Either that, or again, just someone's novel idea on how to accomplish something. This engine, with its 90-degree V configuration, would also have no dead center to it, so you wouldn't be able to, it wouldn't get stuck if you were to turn it off and then turn it back on again. Again, made in Providence. Says here the corner of Gaspee and Francis Streets, and from a printing machine engine, 1870 rather. Granger Foundry and Machine Company. This is the only mention I've ever heard of that company. I don't know of them for any other reason in the Providence area, but I've never actually taken any time to research that either. Just a very unique design, and something we're happy to have here, showing something a little different here amongst the engine collection. Otherwise, I gotta say, may as well mention it, otherwise this engine is identical to all the other ones. You know, it functions exactly the same. You can see here the
Well, start up this way here. The crankshaft, of course, connecting rods swinging back and forth. Crosshead there to keep the motion in a straight line. Piston rod down to the cylinder, and the valve rod with valve eccentric up on the engine itself. So they all work in similar ways, just slightly different configurations. There's a very unique one for sure, the Granger engine. All right, here we are at the old Harris engine. We have two Harris engines here. This is the older of the two, from 1892, made in Providence. First thing on all of these engines, probably been said before, for starting anything, is to go around and, there's dozens of small locations here that all require a little drip of oil. The valve mechanism in particular is littered with these little oil wells. So any engineer would have to go around and oil these numerous times throughout the day. These engines run fairly infrequently here, so whether we're over-oiling them, I guess that's the key. You'd rather over-oil them than under-oil them. I was already able to preheat the cylinder. So this is relatively straightforward here. This engine, the family that donated this engine to us, probably some 25 or 30 years ago, or better, is still in touch, and we do still see the son of the family here at Steam Up pretty frequently, and I catch him around with a bunch of the other steam museums throughout the area. So great to see him and the family still interested in this type of thing and out there at the other museums. So this engine runs absolutely fantastically. The valve gear here, it's a variant of the Corliss valve. So the interior, the functional part inside of the valve is virtually identical to a Corliss valve, where it only wants to rotate through a small motion, or maybe backing up a little bit. The valve eccentric from the engine is conducted through the connecting rod here. The Corliss, you might remember, is down on the floor, but this one is the same exact thing here, connecting to a wrist plate, and this wrist plate will rock back and forth. The internal portions of the valve goes through a very, very similar motion. We have dash pots here to snap those intake admission valves back closed again very quickly. The only difference, and I believe this is a Brown valve gear, is that rather than kind of that bell crank type thing for the trip off that the Corliss design uses, this has this disc, this cam disc, and the governor will rotate that disc that has a little detent in it with a cam follower, and as the roller goes through that cam profile and hits a step, it then trips off to tell the valve gear when to trip off. Let's get her going. This engine actually starts incredibly easily. One challenge with this engine is that the wrist plate can actually over travel, and one of the valve linkages goes backwards and then jams itself. So we want to make a limiter basically on how far that can travel at some point in time. As long as we're a little careful, it works out just fine. So here we go. Real simple. Start putting some steam into the cylinder. Of course, override the valve here, and as soon as we get enough motion out of it, I can drop on the connecting rod here, the valve rod, and she'll get it going. Now, if I remember right, I think we just need to go this way here. And there she goes. Now you can see we actually have a fair amount of water coming out of this engine. I probably could have warmed it up a little bit more. You can see how quiet it runs actually. This is great. Part of the Corliss design effectively, and now the adaptation thereof on this one here, is that it wants to drain all of the water out because the exhaust valves are at the bottom of the cylinder. So it wants to drain all that water out the exhaust on the stroke. Yeah, so let's just take a quick walk around and see the parts of the engine in motion. See the builder plate, William Harris, again 1892 on this engine, right in Providence. One big advantage of doing these on YouTube and videos is we get a real up close and personal view of some of the engine parts. Crosshead here, we would normally have this area barricaded off so that you can't get in place while it's running. So smooth and gentle the motion of these engines. Now, of course, this engine, a little bit different from the other ones. I believe almost all of the other engines have a disc crank throw here. This one still has the original oblong crank for the crankshaft. One very unique piece is the banjo oiler. So this is delivering oil to the connecting rod pin at all times, and that ball is just floating there. It's bolted solid to the crank pin, and we're dripping oil into that ball via the little stand here. So occasionally a little drip of oil will go into that ball and travel up the tube and be delivered to the crank pin on the ends. See, of course, some of the other oiling system here for the main bearing. 3 drippers across the top of that cap. I've thrown some oil in there previously, so that one is actually off at the top. Probably not the most recommended way to do it. Another dripper there on the other side with the cup that you see dripping oil into that valve eccentric. Engine's running a little slow right now. They certainly demonstrate much better running slow than when they're going up to speed. Probably not too much beneath the speed. Probably over half of the standard RPM anyway. Of course, this face here, not only serving as an inertial damper, the flywheel serving as an inertial damper for the engine, an energy storage, but the belt transmitting rotative force up to the line shafting in the building would be placed directly on the face of the pulley here. Let's head back over the valves. And I suppose you see, turning right around here, you see some of the similarity to the Corliss. Rather than this rocker mechanism, we have a disc for a wrist plate on the Harris there. This all looks very similar. Dash pots, the trip-off mechanism, the brown valve here, like I said, is a little different on that, but otherwise the motion and the action is all exactly the same. Let's go back and take another look at that. So as I say, all very, very similar. It works in exactly the same way that the Corliss valve here does. The biggest difference being this little plate for the trip-off. You see the finger still tripping off of the valve and letting the dash pot snap it closed. Dash pot, just a vacuum action here. Let that slip off and snap back closed again. Exact same thing going on the cylinder on the other end. But the time at the stroke at which that happens is all determined by this plate here. And it's connected directly over to the flyball governor. And if I just override the governor a little bit, we'll see that plate rotate. Now if we head back there and you see that plate, if I move this just a little bit, you see the only thing that it does is it rotates that plate. And that other connecting rod goes to the plate that's on the opposite end of the cylinder. And that will simulate either a higher or lower load on the engine. And what it does is, maybe I can simulate it. Let's get a little more speed out of the engine. Always possible that the boiler may have shut off. Let's see. Seems to be building a little bit of speed. Yeah, we're definitely very interesting to see the pressure gauge. I can see a pressure gauge on the wall over here. You can see it varying a bit with the admission of steam to this engine. So there's so much flow going in and then stopping quickly enough. You can see the pressure in the line going up and down. So we've got just a little more speed out of it now, a little more inertia in there just to let me demonstrate what I'm going to demonstrate without shutting the engine off. If you pay attention to the amount of time, that one there actually seems to be a bit more reactive to what's going on. So if we just watch the amount of time that spends lifting before it trips off, then you'll see that plate rotate. And now immediately, notice how much shorter the lift is. I'm going to give it a little more speed, or a little more call for speed, and it lifts much higher. There you see the length of that, or the duration of that emission stroke there going very high. And then immediately I can change this in one stroke to go to a very, very short duration of emission. And that's what made the Corliss, and in this case the Brown valve gear, so much more efficient than earlier designs. It's just that ability to change how much steam was emitted on every single stroke. So let's slow it down. I think we're ready to wrap this one up. It's the old Harris, runs beautifully. While the show is going on outside, I have a great deal of learning yet to do here at the museum, but I wanted to take this opportunity to thank everyone for joining us and for the dehumidifier for kicking on right now. While the show is going on outside, I found a quiet spot to buckle down, do a little reading, and hopefully learn something around here. While the show is going on outside, I found a quiet spot, and I've got a great deal of learning yet to do. I want to thank everyone for joining us here today for Steam Up 2020 at the New England Wireless and Steam Museum. Steam Up is our annual fundraising event here at the museum. It's unfortunate that people aren't able to join us in person this year, but we're happy to bring it to you via YouTube. I hope you're all enjoying the show today, and for anyone who's able, I hope you'll consider making a donation to the museum today. Follow the link in the comments down below, or go to the museum's homepage at www.neewsm.org. The museum is entirely operated by volunteers and funded by your generous donations. I hope you'll consider one today. Again, thank you for joining us, and thank you for considering a donation to the museum today. Here we are upstairs in Station PJ with Mike again. We'll talk about the Massie transmitter.
Okay, so this is a spark transmitter, sometimes referred to as a spark gap transmitter. This is circa about 1907, a product of Walter Massie, one of our local radio experts from the Providence, Rhode Island area. And we'll give you a little tutorial on how this works and how it was originally set up. So we need a power source, which we saw earlier with the Edison Lalande cells, and we need a high voltage source to make the radio. And we use a transformer to change the low voltage to high voltage so we can run the transformer. Unfortunately, we didn't have a Massie transformer, so this is a Marconi And if Massie ever knew that we had Marconi equipment installed in his radio station, he'd be more than a little irritated. Since this was originally DC powered from the Edison cells, we have to convert the DC into some form of AC so that we can run it through the transformer and get high voltage out of it. This is a interrupter or chopper, whatever you want to call it, and this would have the battery circuit wired on these two, and it goes to these big contacts right here, and then it would go over to the primary side of the transformer. This one has a little set of coils here that run these coils, so this works more or less like a doorbell, so that this will go like this and turn this contact on and off, which turns these coils on and off, and then these big contacts here get interrupted and chops the DC that's coming out of the Edison Leland cells into AC that we can run into the transformer.
Now, I know you did a lot of the restoration on this, Mike, when it came here, because we were missing some pieces.
This was a collection of parts when we first got it.
Because this has all been taken out of the building at some point in time by the Massie family, or somehow or other wound up into the Massie family's hands, and then re-donated to the museum.
Redonated to the museum.
So we could have it back.
My understanding is the Massie family had a lot of rental real estate in the area here, and they used to stash Massie radio things in their real estate. And if they sold one of their rental properties, they had to clean it out, and then we got all the radio stuff that was in it. And that was one of the loads of equipment that we got. So this is a capacitor, but none of the glass plates were in it when we got it. So we had to reconstruct all of the glass plates inside of this to make a capacitor. This is an inductor that's part of the system. All of these shiny bits that were on here were missing, but we had drawings for what they were supposed to look like. We were also missing the electrode that's in the inside there to make the spark gap. So Rolf Richter, one of our volunteers here, made all of these pieces, and these are nickel plated, not chrome plated, which is period correct for this. We said we have the Marconi coil in here that we shouldn't have.
Just don't tell anybody.
This is a period correct Massie key, pump handle key. And the contacts in this are very large for the high current that you would need coming from a battery. This is an antenna changeover switch. This is the receiver for this system. And the transmitter and the receiver are both connected to the same antenna. And if we allowed the high voltage from the transmitter to get into the receiver, it would be pretty destructive to it. So this changeover switch here, this is the little wire here that goes up to the antenna. So this little wire here, while you're transmitting, has actually got 15,000 volts on it. And right now, with this connected like this is connecting the antenna over to the receiver. When we want to run the transmitter, we flip this down here, and that connects the DC, the power source for the transmitter, and disconnects the receiver from the antenna so we don't catch the receiver on fire.
Technology of the time.
In this particular case, we don't have a large DC source for this, so we cheated a little bit. We're running 110 volts or 115 volts, 60 hertz AC into the transformer on this. We put a relay inside of the box here so that we don't have 110 volts going to the pump handle key. That would be more than a little dangerous.
Because normally, in its normal operation, you would have full
DC.
incoming DC power voltage on the gap.
And probably relatively high voltage. It wouldn't surprise me if it was in the 100 volt DC range, which could probably stop your heart if you got your fingers across it. So we put a relay inside of this to make it safe to operate, and connected it up to the changeover switch. So the way this thing is wired, we have these high voltage cables. This was yet another restoration project that we needed some high voltage cables, and you can see these ones are some of the few that we had, and they're silk covered. with rubber or gutta percha or something kind of insulation in the inside. We didn't have enough high voltage cables to make this. I prevailed upon some of my friends at Fermi Labs to donate some high voltage silicone cable, but unfortunately they were white and didn't look quite correct on this. And the wife of one of the volunteers here took some Lycra bathing suit material that was this green and sewed them into little sausage skins that we stuck over the white silicone. So they look nice and they look fairly period correct.
Very nice.
The high voltage coil and the capacitor are wired in parallel, and then this inductor that's here, sometimes referred to as a helix, is wired in series with the spark gap that's in there, and then the two of these are wired in parallel with the capacitor and the coil. So what happens is we have AC, 110 volt AC coming into this. And then this is going to pump the 110 volt AC or 115 volt AC up to about 15,000 volts. It's AC, so it's a sine wave of high voltage that's coming out of this. And that's going to charge up the capacitor. And eventually the voltage is going to get up to a point where we're going to hit the breakdown voltage of the spark gap that's in the inside there. And that's going to jump across the air gap that's in there, and it makes plasma in the inside, which is pretty much a short circuit. So now what we have is the helix, the inductor, and the capacitor in parallel with each other, making an LC circuit. So this will actually oscillate as it takes the energy that's stored in the capacitor, and since this is a short circuit across it, it's going to try to dump the energy out of the capacitor into the inductor. And inductors behave like rubber bands, more or less. So this will store the energy for a brief period of time, but doesn't want to stay that way. So it's going to give it back, and it will dump the energy back into the capacitor. So this will oscillate back and forth between the two. And with this particular setup, it's going to oscillate around 350 kilohertz.
Excellent, that's exactly what I was going to ask. Okay.
And that's the RF frequency for this transmitter. I made the glass plates in here. I still have 30 more to make. There's an empty section down there for the piece that I haven't done yet. Once I do that, it will reduce the resonant frequency of this down to about 300 kilohertz, where it was originally designed to operate. This connection here goes up to the antenna, and this is actually siphoning off a little bit of the energy that's oscillating back and forth between the capacitor and the inductor on this. And since this is 350 kilohertz right now, it's RF, and this goes out through the hot wire ammeter and an anchor gap and out to the antenna. Just a word about this anchor gap that's in there. You can see that there's just a little bit of a gap in the connection on there, and Marconi had a patent on having an antenna, an inductor, and a ground in series with each other. And this breaks the DC circuit and gets around the Marconi patent. So this is actually a very common thing to add. And since the gap on this is very, very small, with the 15,000 volts going out to the antenna, it's pretty much invisible. And then this little wire here is on the other side of the gap, and this is what's bringing the receive side over to our receiver. So if I press the key on this, if you watch the amp meter on here, we're going up to about 5 or 6 amps of current running out to the antenna. So, and at 15,000 volts, that's a massive amount of energy that we're pumping out onto that. We have the light bulb across the inductor on here, and only across a small piece of it, to siphon some of the energy off. There's no antenna hooked to this, because if we had that, we'd probably open every garage door within several miles of here. And the FCC would be more than a little irritated with us. So we have no antenna connected to it, and we just have a light bulb on it to absorb all of the energy that's coming out of this.
Now, when I was doing just now, I can feel the vibration of that in the camera grip here, it's got to be dispersing so much energy into the atmosphere that it's causing some sort of vibration here in the motors of the camera mechanism.
Yeah, you also
And
said you had some difficulties with one of the other cameras.
when I did the spark gap downstairs, it turned the camera off several times.
Yeah.
So there's a lot of energy being dissipated into the air here.
Yeah, the other thing is that there's no antenna tuning circuit on this, because this is 1907 vintage, and that came quite a bit later. And this kind of a transmitter was actually banned by the FCC in the early teens, because this is the original implementation of broadband communications. This is all frequencies
Very
all the time.
broadband. Yes.
So later versions of this actually had another coil circuit but onto the antenna to narrow the frequency range that would actually make it out onto the antenna and be kind to things. So I had my car radio tuned somewhere in the neighborhood of this, and it can pick it up no problem at all. Probably about 30 feet away with no antenna on it. But you don't have to bother to tune an AM radio to pick this up. This is all frequencies all the time.
Decimate all frequencies all the time.
This is the receiver side of this. This is a Massie Resonophone. And we cheated on this a little bit too. This is a little 1N914 glass diode that we've got on there for what's referred to as a detector. It's really a diode. And there are quite a few different technologies that were used for the diode. And on all of these AM radios, even on Boy Scout crystal radios and things, you need some kind of a device in there to rectify the RF current so that you can listen to it on the headphones. We put a diode on there because it's reliable and it works. Walter Massie used two sharpened carbon blocks with a rusty needle held in place with a horseshoe magnet.
I think we have one right in the case over here. You know, I know a lot of people had different ideas and different methodologies that worked on rectifying that voltage with the detector. So
this is one right here. You can see the horseshoe magnet holding the needle in place. I have absolutely no idea how that works, and I'd be really pleased if somebody in the audience could give us a clue as to how that's working.
any chance that you get a magnetic current through the wire when it's flowing in one direction, but then in the opposite direction, it actually reverses that field and wants to push it up away from the...
I don't know. I always thought that the magnet was there to hold it against the carbon blocks and keep it in place, you know, like as a ship rocked or something like that. But you may have an idea. There's another anchor gap that's inside there.
Interesting. Quite the collection of Massie artifacts that we have here. And I know we'll be back to talk to Lynn in just a few seconds about quite what all that is about. He's the Massie historian here.
Now there was another kind of detector or diode that a gentleman named Reginald Fessenden came up with, which he called the electrolytic detector, that had a small cup with a platinum wire in the bottom and a platinum wire touching the surface of some dilute nitric acid that was in it. And again, I have no idea why, but that makes a diode, and apparently it works better than rusty needles and carbon blocks. So it was common for the radio operators to bring their personal detector with them and potentially plug it into the Massie one there. And if Massie ever came around, you'd quickly take your electrolytic detector off and put your carbon block detector on there so you wouldn't get in trouble with the boss.
So what's the list? We have the galena.
Yep.
Right, galena. These various
Germanium, acid, carbon blocks, silicon, carborundum. I mean, there's
the rusty razor blade, or the oxidized razor blade with the wire against it. They all do the same thing as a diode.
Yep.
A one-way valve.
Yep. So when you look at the conduction curve for any kind of a diode, they have what's called a knee in it. So if you look at the current flow versus voltage across the diode, the voltage will go up and up and up with no conduction, and then you'll see a little bit of a knee in it as it starts to conduct, and then you'll see a conduction path go up.
And if you look in the data sheet for a modern diode, you'll see that knee in there. So this would have a battery connected to the headphones and the diode on it. And this is connected to a resistor on here. And what you were supposed to do to operate this was adjust the current that's going through the diode, and you would adjust this back and forth until you heard this scrambling eggs noise in the headphones, so you knew that you were on the knee of the diode.
Is that a technical term?
That's a technical term.
All right.
It's actually in the literature. And then you would back off the current just a little bit, so you're below the knee. And the diode was connected to the antenna, so when you started getting RF energy in, it would push the diode up the knee in the conduction curve, and then it would activate the headphones on this. And this has also got a inductor and a capacitor in here as part of the tuning circuit that's on it. So in this particular case, this radio has tuning capability on it that the transmitter doesn't have.
Gotcha.
So you would set this up for a particular inductance and capacitance for the tuning circuit, and then you would fiddle with the resistance on there, and then you're good to go. And you would hear the in this case, Morse code, the telegraphy in that. Now, another note on the way that this works, that the headphones obviously can't react to the 350 kilohertz for the RF on this. And
It's just much too fast of an electrical signal for both the human ear to hear and for any sort of a electromagnetic device to react to.
Right. So the diode on that actually rectifies the 350 kilohertz RF signal, and that will give you more or less one pulse that goes into the earphones. And since we've got AC going into the transformer, the output of this is going to oscillate plus and minus on the high voltage. So this is going to go from 0 up to some higher voltage and arc. And since we're peeling off some of the energy, either for the antenna, in this case for the light bulb, it causes what they call a damped oscillation. So if you look at the oscillation on there, it starts out big and then tapers off quite quickly. But that the envelope of that damped oscillation is what's activating the headphones. Now, 1/120th of a second later, because we're 60 hertz in this country, the capacitors are going to get charged up again, and then we'll go through the same damped oscillation again. So what you actually hear in the headphones on there is this 120 hertz repetition rate of the damped oscillations on this. So it sounds really awful. You can go on our webpage, there's a recording of what this sounds like, and I can't believe that they can actually get any intelligence out of it. But they did.
And that was true of all AM. That's how AM works in general. It's not something specific
That's
to
correct.
Massie at all.
That's correct.
Right.
So it's the envelope of the RF that you're either running the speaker or the headphones
Yeah,
with.
absolutely.
Now, another note on the construction of the transformer on this. This is what's referred to as a pi-wound transformer. And the insulation that they had for wire 120 years ago wasn't particularly good. And it was nearly impossible for them to make a modern design of transformer with the insulation that they had available at the time. The insulation just didn't have the resistance capability, and it would burn through the insulation if we tried to put 15 kilovolts through it. So in this particular...
15 kilovolts for anybody out there. 15,000 volts.
Yeah. So this particular transformer, instead of being wound in the normal manner, where you would have a core and you would wind the primary side that goes over to our battery, and then the high voltage secondary side right on top of it, in that case, the secondary side might only be an inch thick with the wire. So we'd have 15,000 volts over an inch of insulation, and it would probably just burn right through it. So what they did was that instead of making the coil long and small, they made it narrow and thick. So this is actually the outside of the high voltage layer, and there's a low voltage layer on the inside of this. And then there's a number of these that are all wired in series, and then up to the output on this. If you damage one of these, then you can just slide this whole assembly out of the rack in here. You can unsolder the connections between the coils and slide off the damaged coil, slide a new one back on, solder it in place, and plug it back into things. So if you shorted out this coil from a high voltage problem on it, it would probably take you all of 10 minutes to repair it. They had the same kind of a problem with the glass that they were using for the capacitors. The original glass that was in this is what they referred to as flint glass, and 120 years ago the quality of the glass wasn't anywhere near as good as it is now, so it was common to get carbon inclusions, little bits of carbon inside of the glass. That's half the reason why this is 1/8 inch thick glass, which is twice the thickness of ordinary window glass. So it was common for them to actually burn a short through the carbon inclusion in the glass and short out the capacitor on this. And they would either, you can just undo the thumb screws on this and slide a glass plate out, or the literature says that you can take your penknife and just cut a circle out of the tin foil on there around where the short was and put the glass plate back in. So everything on this is really designed for high reliability and ease of maintenance on it, which is pretty clever for more than 100 years ago.
I suppose you have the same problem enough times and you figure out how to work around it, how to make it easy to solve on the fly, because I'm sure they're getting paid based on, you know, how many messages they can send or something like that, so they need to be up as much time as humanly possible.
Yep. On the wall over here, we've actually got some pictures of the ships that Massie had equipped with the Spark radio. So these were ones that were running more or less from New York City up to Rhode Island and Massachusetts. And eventually Massie had stations pretty much all over the world.
Very cool stuff.
I'm standing in front of the Massie Wireless Station PJ. The PJ stands for Point Judith, and this entire station was down on the beach at Point Judith to communicate with ships passing by Rhode Island coast. People would actually, businesses would actually hire the station to get in touch with the ships, their ships that were coming in, so they knew when they were going to arrive in the Port of Providence, and they would be able to be ready to unload them and whatever.
Neat. So this whole building was moved up from Point Judith?
Right. In 1983, Bob Merriam and a group of volunteers moved this entire station, I believe it was 4 pieces, up from the coast to here where it is resides at the museum now.
Interesting. Want to head inside and we can take a quick look around?
Sure.
Great. Very cool.
So the station is 2.5 floors, 4 rooms. So the wireless operator actually lived here, you know, when the station was active. The station was active from 1903 to 1910, when at that point Marconi bought the Massie system from Massie. So these downstairs rooms were living quarters at that time. Right now we have some wireless equipment down here that
Some wireless equipment. I mean, it looks like a boatload to me.
right.
That's the whole museum, though, just some wireless equipment. Interesting. What do we have going on over here? Craig, actually, I think I know you're more of an expert in what this is all about, so if you want to jump in, that would be great.
Well, the radio portion of this building was upstairs, but we accumulated here over years some a lot of ham radio equipment with some original tuning coils and radio tuners, just equipment in general, meters, and it's all working equipment. But today we actually use a modern piece of equipment right here. This does what all that does. As you know, that happens. So it's a little safer to use. But we try to activate the station, which is now called N1EPJ. We obtained this call sign not just a couple of years ago when we tried to preserve the PJ, which is Point Judith, and this building's radio call sign was PJ back in the early 1900s. So now we have N1EPJ, and that's the call sign of the radio club here at the museum.
Neat.
So we're going to try to keep the station alive and activated as N1EPJ, and hopefully some year we'll have what's known as Field Day operating from this building in the grounds as soon as that's possible.
Great. So just a whole collection of radio stuff down here between gear and active transmitter, you know, some QSL cards from the, you know, who knows, do you know whose collection these were from? They're not from the station, are they?
I don't believe so.
Okay. I can see a familiar one down here immediately. Bob's.
Oh, W1NT.
I've heard of that guy before. Nice.
Miriam's call sign.
Yeah. All right, great. Let's take a look upstairs too, because that's of course what the station is all about. Talk a little bit about Massie himself.
So this is the second floor of the station. This is actually where the main transmitter was. As you can see over here, there's a big pump handle key. There's a little controversy about this. We were told that it was for cold weather, but it just doesn't seem like it fits, because you know why would they have it at PJ? But this is the key that is here. All this equipment actually, luckily, was stored in a farm in Rentham by Massie's relatives. So once they got the station here, they actually donated the equipment back to the station, and
Great.
we have it all.
Yeah, we've talked with Mike a lot about the details of this equipment already. Anything about Massie himself? I know you're kind of the expert in that. So then we have a whole array of artifacts here. You know anything about these that we can talk about?
Well, these are actually transmitters, you know, in kind of like portable form.
Okay.
There's 3 of them here, 3 or 4 of them here actually, and if you notice, a lot of the similar components here are also here at the station.
Gotcha.
Like that antenna switch, which was a Massie design.
Yep, I do remember seeing that. Mike talking extensively about that over there.
Well, if you look down here, that block that says Massie detector, actually it was a needle that sat across those 2 metal black carbon
yeah.
pots you see there.
And
we actually have some of the original needles right there.
Yeah.
And then the filings they use for the equipment, they actually use nickel filings, and we actually have some of the original pieces of nickel that they used to
from the station here.
From the station, right?
Interesting. Now, I know some of this display is, of course, about the building being moved here. You know, the physical move of the building here.
Right.
But
we also have an original picture of it out on Point Judith at the end.
Oh,
there.
right.
And then Massie also equipped the whole Fall River line of steamships, which there's a picture of one right there.
And the original purpose, I'm seeing it right in front of me in this book here, the original purpose of the station at PJ, if I'm not correct, was all to communicate the news out to Block Island. Is that right?
Right. In 1903, there was a paper called the Block Island Wireless, and they had a station on Block Island and this station, and they would transmit the news each day out to Block Island, and there they would print the paper and pass it out to the Block Island residents.
Interesting.
It only lasted 1 year. I think it was just about 40 issues, one summer.
Huh.
Actually, 40 issues, and that was owned by the Providence Journal.
So interesting to think that they went to all of this extent for the sake of communicating the news out there.
Right.
When, I don't know, 11 miles or whatever it is, like they could have taken a boat, but obviously everything about life was so different. There's the boat, having to sail potentially out there because steam power was still in its infancy and so forth. So this was somebody's better idea of getting the news just 11 miles offshore.
And that was actually the second wireless newspaper. The first one was out in California, so the second time it was done in the country was this station.
Neat. We have one of the largest Massie collection around here. Is that correct? Or
Yeah, I think that's correct. Yeah.
I mean, not only the station itself, but between some of the other salesman's models and so forth here. And I don't think we'll get to it today, but I know we've got Massie's workbench from his workshop in the shop in storage.
Yeah, we do.
Just a whole collection of Massie equipment and so forth here. Do you remember the story with this thing here? I know somebody said his grandson had told us that this was a toy.
Right.
If I remember right, that he had put together for his grandkids. I think it's basically an engine powered by electromagnetic solenoids that Massie had put together for his grandkids or something.
Right.
If that's right. So even some of the family stuff has wound up here through the years, through donations and so forth. Really a very interesting collection.
Over here we have the telegraph station because, they communicated with the ships at sea with wireless, but to communicate to Providence, say, or local cities, they used telegraph, and that's what the station is right there.
Gotcha. So messages would have been received on the wireless from ships potentially here if they were able to communicate back and forth,
Yep.
and then distributed on the wired telegraph network here.
Right.
Understood.
Yep.
Makes a lot of sense. All right, that's great. Well, thank you, Len, for a little bit of background here. Appreciate it. And as with everything here, there's so much more that can be told and seen, and hopefully people can get back here next year to actually see things in person. All right, let's head over to the steam building, I think, and see quite what's next. Here we are with the Harrishof engine. It's a very unique engine in our collection. Again, made in Rhode Island by the Harrishof company down in Bristol, Rhode Island. But it's the only triple expansion engine in our collection. Triple expansion, it has 3 pistons, 3 cylinders. Took advantage of expanding the steam 3 separate times. Smaller piston, 10-inch diameter, 15-inch diameter, expanded a little bit more, gave you the same amount of power, just lower pressure, and then a 20-inch cylinder, expanded that 3rd time. Try to make it as efficient as possible. And this engine here is actually the most powerful one in our entire collection. It rated at 385 horsepower, and yet is incredibly lightweight compared to all the others. I'm sure some might not think it looks lightweight, but I guess if something like this is your point of reference, that flywheel alone weighing 20,000 pounds weighs more than this entire engine would. So Harrishof, of course, is a well-known name in the yachting world, most famous for his America's Cup yacht designs, building yachts in general, but people might not know that he actually started working for, Nathaniel Harrishof, of course, started working for George Corliss in Providence before founding the Harrishof Manufacturing Company, and got his kind of cut his teeth on steam engineering, working for Corliss before venturing out on his own. So it's a very complicated engine with all the moving parts, of course. 3 cylinders, 4 valves, 3 crossheads, 3 connecting rods, all the bearings associated with that. You see the complexity of that crankshaft back there with all the counterweights on it. The valve shaft in the front here, a lay shaft with the 4 valves, their respective connecting rods and the valves up inside the cylinders here. All of these bronze pieces, I suppose it's a little nod to his
his marine engineering. Those bronze pieces are the transfer tubes to transfer the steam from the high pressure to the mid pressure, and then the mid pressure again to the low pressure cylinder, shuffling it on down the way before making its way out the exhaust. Now this engine was similar to something that Harrishof had designed and installed for naval torpedo boats back in the day. This engine was built in 1904, but this one actually never was put in a boat. This was used on land for Phelps Dodge, running a direct coupled generator, generating electricity, and ran in the New York City area for 70 years, producing electricity from 1904 there until 1974 or so. So it's fairly noisy with all the moving parts, and I gotta say, some wear on 2 of the gears here. There's a couple of spur gears connecting the crankshaft to the valve shaft there, and there's one particular spot where the force changes direction, and after running for 70 years, it's definitely worn quite a bit, makes a bit of noise when it hits that spot. So you see some of that internal complexity there. Let's get it running. I've had it running, I've got it all warmed up. We should be able to just open the valve and let it go, see what happens here. It's quite a fascinating piece. Now I can say, I hate to make this reference, but I can say the triple expansion, there's some people out there will recognize the triple expansion engine as being the style that was in the Titanic. And that would be probably the best known triple expansion engine out there. The Titanic engine had 4 cylinders in it. I believe it was 1 high pressure, 1 mid pressure, and 2 low pressure cylinders. And even from there, they were able to take the steam off and feed it into a turbine for the center propeller there. Still actually utilized some power even after it came off of the 3rd expansion. So this engine has no flywheel on it. It was coupled to a generator, as I said, and the generator provided some of the inertial dampening that would help the engine to run a little smoother. You can hear that high-pitched knocking there. There's the chatter in between those, in the teeth, in the gear teeth. It will go faster. We don't want to run it any faster there. It's actually much easier to see everything at these lower speeds, and that's true of all the engines in the collection. We have no need to run them particularly quickly because everything is actually easier to see at lower speeds. And I'm hoping to get to these gear teeth this year. Be able to get that off, cut a keyway in a new location, and reposition the gear on there to get away from that worn spot. Try to eliminate that noise. But it is a very interesting piece. It does actually have an oil sump down there, partially enclosed like this. A lot of the Harrishof designs were actually of very, very similar style. Were designed as open crankcases, and of course I know that was very typical of the larger marine engines anyway, just to run the open crankcase and have to oil everything directly and kind of have everything oil land in drip pans and so forth on the ground. But otherwise, other than the triple expansion, of course, this engine is very, very similar in its operation to many of the others. All the cylinders are double acting. We've got steam feeding in, would have a governor there up on the inlet valve assembly. Steam goes through, in this case, 3 separate expansions before exiting the exhaust. piston valves in this engine. Round piston valves able to move, open very quickly through a short sliding motion to open a large surface area. I can see the valves there moving only about 2.5 inches or so from fully open to fully closed. Or actually I should say from, open on one side to, reversing direction to open on the other side. Maybe 3 inches. So a very unique piece, like I say. We do have a model of a triple expansion, but there's really nothing like seeing the real thing run. So there it is. Like I say, one of the most unique pieces here, the Harrishof triple expansion engine, 385 horsepower. Let's see what's next on the list today. Now spinning right around here at the museum, we have the Harris engine, another one of the large mill engines here, and it does something very special. It's actually incredibly similar to the Corliss in what it achieves, but was done in a very different way. We happen to have one of the steam chests here apart right now to get started for the day, so it's going to be very easy to show what it does inside. And we may as well do that before we fire it up. A very unique chance to see quite what goes on inside some of these engines. Of course, an oiler here and so forth. So let's take a quick look right down here. You may recall the action of the Corliss valve, where it has the ability to open the valve. This would be one of the admission valves from the Corliss, or similar type to the Corliss. And the valve seat, or the valve opening, is this very long, narrow slot. And you may recall from the operation there, we will actually be showing it immediately after this engine here, that in order for this valve to open, within its seat, all it does is just rotate a slight amount and then snap back closed again. So again, with the valve seat opening only being 1.5 inches wide here or so, when this rotates in its seat, the steam is able to flow directly through the valve and down through the other side, and then it can snap back closed again very quickly. So it has a little rotating motion. Now, the green engine does something very similar. It has the functionality of the automatic cutoff and the variable cutoff. The mechanism is entirely built into this setup right here, and it will be much easier to actually show this when this engine is running. Unfortunately, there's no way to decouple the actual slide on this engine from the eccentric, crank eccentric there. So, this is an example of that. What would happen when this valve opens, what goes on here is that this bar oscillates back and forth like this, and these wedges that you see here are controlled by the governor. So the governor on this engine actually just raises and lowers these wedges, and what that does is it gives you a geometric difference of distance between here. As this rocks back and forth, as this piece moves back and forth, it lets it slip off at a different point in time. But let's go see what's going on inside. That would snap close quickly normally. Let's go and see what's going on inside the engine when we do that, to see how that motion actually produces the large opening, and very quickly, similar to the way that the other one, the Corliss, does. So we've got one of the steam chest covers off here, and this is the valve itself sitting on its seat. And backing up a little bit so you can see what's going on. If I move this lever here to open what we just did, we will get rotation of the crank over there, and it pushes that push rod right straight through. And then you see the grate type mechanism inside there. So with just that little bit of sliding motion, we go from close to completely open right there. And I don't know if we can get a little reflection off of it. Let me tip down here a little bit more. I think we can see it. Deep inside there, that object down inside is actually the piston rod. So we are looking directly into
the end of the cylinder, and you can see the piston rod deep inside, and then that snap closed. So you get the action of it opening up a wide area in a very short amount of motion, snapping back closed again relatively quickly, and then again, all of that motion derived from the pivot of this arm on that end of the cylinder, and then similarly another one for the opposite end of the cylinder. Let's get this engine back together again, get it running.
Okay, we're going to talk about our green engine today. This is another automatic cutoff engine, so you've seen the valve gear in the Corliss and why the cutoff is important for improving the efficiency of the steam engine. The green engine does exactly the same thing with the improved efficiency of the Corliss, but it does it in a very different way. To start off with, we've got these little dogs on here that control how much the valves open, and we can wiggle them for you so you can see how they work. That's lots of steam. This is little steam, and it has one feature on it that's very nice. If the belt that drives the governor on this breaks, the governor will slow down, and the governor thinks that the engine is slowing down and will open the steam valves up as much as possible, and you can get a runaway condition on there, and that's more than a little hazardous. So this has a mechanism on it and a little adjustment on here. So normally this valve gear sits like this, and the dogs will go up and down. If this goes more open, this will eventually hit this, and this pops up like this and drops the dogs in the completely down position, and it will actually shut off the engine. So this is one of the few engines that we've got here that isn't hazardous if you break the governor belt on it.
I've seen similar types of things on some of the other engines, Mike. This seems like by far and away the most simplistic. Yep. They've achieved a lot of things on this engine in a very, very simplistic way. Yep. Now, of course, this is part of the governor. If we haven't said it, this governor is frozen up at the moment, so we've taken the fly balls off to do a little maintenance on it. So it's not actually doing anything, but if it wasn't already obvious visually, that would normally have the fly balls on it, and the whole governor here is what we're talking about.
So to start this engine, if we just let the governor relax and have the dogs keep the valves all the way open, this will actually trip because it thinks the engine has stopped. So we have to put this part in here, and that will hold the dogs quite a bit open so that we can get some steam into it. There's another feature that's on this, and this has got a little steam valve, a steam piston that's in the back of this that can push on this piece of the governor right here, and this solenoid valve here will allow the steam into the piston. And this was connected to a button, a big red button that was in the mill someplace. So if they detected some problem in the mill, they could push the button, and this piston would jump up, and that would push the governor all the way up like that. And if you notice, the dogs are all the way down, so you get no steam into the engine. So you can push the button and remotely stop the engine. At the same time, there's some little electrical contacts right here that were connected to a giant alarm bell that we have hung on the wall next to the Corliss engine that would go off and let everybody in the building know that somebody manually shut the engine down. Now, starting this engine is actually, I think, simpler than the Corliss. We have these little handles here that we can plug in, and this piece here moves back and forth to open the valves, and we can plug the handle in and manually control the valves. We've got these little handles on here that control steam coming into the engine. So connecting rod is up toward the top. This engine runs over, so the flywheel goes that way. So we need to open up the steam valve on this end in order to push the piston down. So that's this valve here. So to get this engine started, let's give it some steam. Open the steam valve. And it's off.
Just like that, huh?
No muss, no fuss. now you can see that the dogs on there are controlling how far the steam valves are opening. They're a little reluctant to close on here, and that's adjustments that are on the dash pots down in the bottom. So we could make some adjustments on that and get these to close a little quicker. I can show you with the engine running, I can manually manipulate the governor. And so if the engine were running faster, the dogs would go lower. If the engine were running slower, the dogs would go higher and let more steam in. And I think we need a little more steam to keep it running here.
Come on, baby. Yeah, of course, just by manipulating that a little bit, Mike, in the demonstration, we lose so much inertia. You know, it actually needs a little more flow. So, you know, it's actually incredibly interesting because basically they've achieved something very, very similar, if not identical, to what the Corliss does in a much more simplistic way. You know, it's crazy. This all seems much more simplistic to me than that mechanism.
And much easier to maintain, much easier to adjust. You know, this piece here on the valve and this piece here on the dog on here are going to be the only wearing parts on the valve mechanism on it. And there's virtually nothing to adjust on this as it wears. So eventually you would have to replace these two pieces on here. And the total time to replace all four pieces that would wear in the governor might be an hour. So the downtime on this engine to do a governor maintenance on it is minimal. Taking the brown gear part that's on the Corliss style engines is considerably more complex than this.
There's our new Harris here has suffered from some binding valves for a number of years now, and I've been reluctant to take it apart for 3 years now just because I don't want to get into it.
Yep, it's a good little engine.
Very neat. And such a simplistic way that it goes about everything. You can kind of see the, you know, of course, the actual valve mechanism in here, or the actuator going directly into the steam chest. Let's just take a quick walk around and kind of see some of the other parts. This isn't a bad perspective here on a very interesting exhaust valve rocker eccentric there, rotating that exhaust shaft back and forth, still with an eccentric, but at right angles to you know, normal operation. This engine happens to have a rotation counter here as well. A very simple mechanism. Suppose that could have been used for maintenance or something to check up on how often it needs maintenance. Again, the exhaust eccentric would be the one to the left here, and it's doing a very interesting motion because it's being used very, very differently than any of the other engines in the collection. You see down below here, it's actually actuating something vertically. This rocker rotating shaft here with a little crank. Totally different than any of the other engines. And Mike, what's the story with our oiler over here? This seems so exotic.
This is kind of an interesting mechanism on it. So this is a standard grip oiler that's here. So when we open the needle on this will drip down into here. The oil collects into this, runs down this little pipe on here, and then collects inside of here. When this pipe is down like that, the oil will run down and go into the big end of the connecting rod.
It's so simplistic. So this isn't connected at all.
Nope, just dangling in there. So the oil will just drip into this piece here. And since it's spherical on there. It will stay inside there until it gets down and drips down.
Sure. I will say, thankfully, I put some oil in the cup before we got started, so we for just a little run today. I guess you probably don't get the chance to get this close to a industrial steam engine too often. It's amazing. It's so gentle, so refined. You know, I don't know. I would imagine that people have this perception of old-time technology as being crude and noisy, rough.
It's not a diesel.
It's not a diesel, that's for sure, yeah. Having driven one for 20 years, I can attest to that.
Most of the people that visit here are just really amazed at how quiet and smooth these engines are. This is another interesting feature that's on this. This is another kind of oiler here. So this is another drip oiler, but it'll drip, and there's a little wick down on the end here. So this will eventually get a drop of oil sitting on the end of the wick, and then the crosshead comes over and picks it up and oils the crosshead on it.
Engineers found very, very simple ways to achieve, you know, what they needed to do rather than these incredibly elaborate mechanisms. Of course, the Corliss has that very elaborate extending rod oiler thing on it to achieve the exact same thing instead of just picking up a drip.
Yep, this is easy.
We've just got a couple little gauges here to kind of get some idea as to what's going on in each end of the cylinder as it's going through its stroke. Mike, tell us a little bit about this engine coming here and so forth. I know that we've got some pictures on the wall right behind you of it being taken out of where it was and a number of things about it.
This is the only engine we have here that's actually been donated twice.
That's interesting. I hadn't heard that story before.
This was in a mill in Pawtucket that made what I believe is called supercalendered paper. So it was very high quality, fine surface paper that was normally used for things like wedding invitations and things. And the building, I believe, was built in 3 separate pieces. This engine was installed in the cellar of in one of the older parts of the building. The newest part of the building had been converted into office space. The back parts of the building were almost abandoned and were leaking water and were in really, really tough shape. It was going to be quite expensive to demolish the back halves of the building, which were actually above this engine. So the original landlord did nothing. He sold the building. He donated the engine to us. We didn't have a way of coming in and picking it up because we would have had to make a hole in the foundation, which probably would have collapsed the fragile building trying to take the engine out. So it wasn't going anyplace. We just left it. And then he sold the building and neglected to tell the new owner that the steam engine that was in the cellar of the building had already been donated to this museum. So we had to negotiate with the new owners to donate the engine again. And that was a little bit lengthy. So eventually the new owner demolished the building. We sent a crew of volunteers in, and they took everything out of the steam engine room that was human portable. So all of the valve linkage connecting rods, anything that was human portable was removed. This engine actually came with a complete set of maintenance tools and brand new bearings. And there was actually a boiler shift rotation schedule still in the wall in there from 1923 when this engine was put away for the last time. Then the crew here built cribbing with some 2x6s over the whole engine, and then they dumped the building on it. So there's some pictures here you can see with the excavator with the demolished building, and they're picking the pieces of the engine out of it. So they use the demolition equipment to pick it up, put it on a flatbed, and bring it down to the building here.
Oh, okay, here's a good one right here. I do see it. Oh, just so much stuff laying around, demolished pieces laying all about. That's crazy. I like this little calculation here. It's something that gets overlooked because it's kind of interspersed with the rest of the display here, but we've got a little math on the wall that's kind of astonishing to think about.
Yep, this is talking about the amount of torque that an engine will make. And with a internal combustion engine like a diesel or a gasoline engine that you've got in your car, a typical car engine might make 200 or 300 foot-pounds of torque. Some muscle car might be up in the 400 or 500. Diesel trucks and stuff will make significantly more than that. But in the case of any internal combustion engine, the torque is achieved about halfway through its maximum RPM range. So that's why, if you've got a manual transmission, you can rev the engine a little bit to let the clutch out to be able to go someplace. Steam engines, on the other hand, make maximum torque when they're stopped. And that makes them very useful when you've got an entire mill full of equipment and you have this huge static load and you need to get all these knitting machines or something like that started.
Every single one of your employees happens to have forgotten to disconnect their own machine from the shaft before they went home?
So having an immense amount of torque is important. So in this particular case, we're talking about 100 pounds per square inch of steam pressure and 225 square inches for the surface area of the, this is a piston ring out of this one, so you can get an idea of that. So it's the radius of this squared times pi will give you the surface area of this. If we multiply that by the steam pressure that we've got on this, 100 pounds is actually small. This would have run at 175 pounds or so. And then you multiply that by half of the stroke of the engine, and we end up with 22,000 foot-pounds of torque for this engine, which is just an immense number compared to what you'd get out of your car.
See, I thought my Toyota was doing pretty good.
Yeah.
No, not so much, huh?
Not
oh, boy.
And it's available with the engine stopped. So if the engine operator were good the night before, he would have stopped the engine with the connecting rod either at the top or the bottom, so that would give him the maximum amount of torque when he went to start it up in the morning.
Yep. Get some vindictive nighttime operator who shuts the engine off at top dead center,
That makes it a little challenging to get started in the morning.
Well, very cool. Again, so similar but to the Corliss, but done in a very, very different and I would say much more elegant way, honestly. Appreciate it, Mike. Let's go take a look over at the Corliss. I know we want to show that for the end of the day here, and
okay.
Let's get to it.
Okay. We're going to talk a little bit about the origins of this Corliss engine. This engine came from Stratton, Maine. There's an advertisement here from the company that we got it from. And they made, like they say in here, turned wooden parts, like pot handles and chair legs and things like that. And this was hooked to a generator that was powering, supplying electricity to run all the machine tools that they had in their plant to make all the turned wooden parts, which in turn make an awful lot of wooden shavings, which they burned in the boiler to make the steam to run the Corliss, to make the electricity to run the machine tools to make the shavings. So they had more or less perpetual motion.
This is some old-time green energy.
Yeah, so it was a really good idea. There's some pictures there showing how we originally installed it. It was actually installed in an addition. This was the end of the original size of the steam building, put an addition onto the foundation, and assembled the Corliss engine actually outside of the building, and then built this third of the building on it. In the latter years on this, it wasn't particularly well taken care of, and but that's why we got it.
Yep. And we didn't have too many choices. There aren't a lot of genuine Corliss engines out there. Certainly lots of other manufacturers, but none right from the Corliss company.
Yep.
Very interesting.
Do we want to run it?
Yeah, let's see it. It's always great to see it in operation. Why don't you go ahead? Why don't you close that valve, Michael?
Sorry?
Close that drain valve there, and we'll. There you go.
Now just running on the bypass here.
Yeah, works great.
So we want to go.
Yep, down.
This way.
Oh, it missed it. Let's see if it catches. There we go. Let's hope it, yep, just in time. For some reason, the valve hook managed to miss its pin on the first try. Gotta say, it still goes pretty effortlessly. You know, you can see, having come from the green, you know, still a beautiful running engine. Smooth, quiet. I would say even a little quieter than the green at the moment, but you know, certainly there's a lot more going on over here, a lot more complicated movement to all of this than what they were able to achieve with the green.
Yeah, and the valve mechanism on this is a lot more complicated on the green. Having a chunk of wood in here to trip the valve isn't something that I would choose. And you can see that there's another brake along here that's been welded. So this has had lots of these fragile little castings broken on this, and none of these pieces exist on the green. So it's simpler and easier to maintain on it. And this mechanism here is actually the second or the third design that Corliss did. There were several versions that were even more complicated and more temperamental. One of them called it crab claw, because it looked like a crab claw on it. And there's some later designs to this that are actually a little simpler too.
It does run pretty beautifully. See, this case, the governor is actually doing its job up there. We've got it overridden at the moment, but simple with the increase in speed, the ball's flying out. It will want to raise this here, rotate the crank here, and then come and rotate this bell crank to move the position of the wood block out a little bit, or vice versa on the opposite end, pull the block of wood in.
Which will mean that this little piece here will fall off earlier, and said this is opening almost all of the way, but this would probably only go up like this and then open the valve just a little bit.
Yep.
And the governor says it's got plenty of steam.
Yep. Still absolutely ingenious for its day, and completely revolutionary because it was adopted by manufacturers around the world, but nonetheless, other manufacturers were able to improve upon it through the course of time.
Yep. One other little thing that I don't think Randy has talked about is how we actually get power off of this engine. And you see that the outside face of this flywheel, if you look up at the top of it, you can actually see that there's it's not flat, there's a little bit of a crown to it. So the center of this is like this. And there was actually a leather belt sitting on the surface of this, and then running off into the rest of the mill. It would either be connected to an alternator or to a generator or to line shafting that ran over the whole mill. And we've got some belts over here. So you can see this piece right here. This is a leather belt from one of these engines here, and this was probably 75 or 100 feet long when we got it, and I can't imagine how many cows that took to make this belt.
I'm at a loss for words, honestly. And I don't know how many cows would have made that either. Funny to consider, but hey, that's what was done, right?
Yep.
Well, let's take a quick walk around because I'd actually like to see the other side of the engine, Mike, if that's all right. Let's see. Everything packed into the building very tightly. Very happy that I can get closer to some of these things than the casual visitor might. Very interesting. I mean, the flywheel pit here has got to be 6 or 7 feet deep. Flywheel sitting, crankshaft here sitting about waist level. You can see the valve eccentric, just a single valve eccentric operating the intake and exhaust valves on this engine, and all of the complexity of the motion is really handled on the other end with the mechanism on the other end, rather than having anything to do with the eccentric itself. Let's keep on going here. Another smaller engine tucked in right in between everything here, making for some narrow passages.
This little Christmas tree looking thing on here is a oiler for the eccentric and for the big end of the connecting rod. So this is the same thing. It's got a drip oiler on here. It would be a drip that will form on the end of it here, and this little wick comes up, picks it up, and oils that. And it's got the same kind of a mechanism over here for the eccentric. You get a drip on there, and the little wick will pick it up, and that's enough to oil the eccentric. These two oilers here will oil the crank bearing on it.
Well, you know what? I had never noticed that the third one, interesting, the third one up top is also for the main bearing, drips down through the middle, and then two separate ones. So there's actually three attached to that main bearing. Very cool.
You can notice that there's a gap between the two bronze inserts here on the bearing, and that's for adjusting the clearance on the bearing. This is actually a wedge here, and we can drive the wedge in to push the two ends of the bearing together. So as this bearing wears over the next 100 years or so, with the amount of work that we make this thing do, we can actually tighten up the slack on it by just driving this wedge in a little bit.
A lot of the things that they were doing at the time simplified both the manufacturing method and provided for ease of maintenance. So they really thought through a lot of these details on how things were made.
One other thing on the big end of this one, you'll notice this has a disc for the big end of it, and this engine actually shipped from Corliss with an arm on it, like you've seen on all of the other ones. And sometime in its life, they retrofitted this with a disc, and that must have been an interesting job because they would have had to heat it to make the diameter larger and then shrink it onto it.
Yeah, because I noticed there's no bolts or anything holding that onto the shaft itself. It's just a shrink fit on there, huh?
Yep, and there's actually an adapter ring in here, so you can see that there's a ring that they shrunk on and then shrunk the entire flywheel on it. So that would have taken a big fire to heat this thing up enough so that it would expand enough so that they could push it onto the end.
And just imagine, I mean, this disc has to be well over 1,000 pounds, and they're gonna heat up to, who knows, hundreds of degrees anyway, thousands of pounds of metal, and then have to handle it in some way to get it on and accurately position it.
Yeah, it must have been an interesting project.
Yep. Don't grab it in the wrong spot.
And there's another clever oiler on here. This will drip down, go through this plumbing, and then down through this tube here. But you can see it's a coaxial tube on here to keep the oil inside of it. It goes down into this little pivoting thing here, and then we'll oil the crosshead that's on it. See a bit of corrosion on the piston rod that's on here, and that's part of life of an old steam engine, and it would be a very large and expensive job to remake the piston rod for this thing, so leaking a little bit of steam is part of the character of this engine.
Yeah, maybe we'll try to repack that at some point in time and see if it improves it, but nonetheless, it still runs beautifully. Just like a giant locomotive, right? A little puff of steam for dramatic effect.
Some character. This is another interesting device that's on this. This is yet another kind of oiler. This is a displacement oiler. So this is connected up to the steam jacket that's in the inside of it. And you would fill this up with oil, and the steam would condense on the inside of it. And since oil floats, the water would collect in the bottom of this, the condensed steam, and it would push the oil up, and then the oil would overflow and go down and, in this case, oil the cylinder on it.
Interesting. I know Ernie talked about it briefly, but we didn't get the technical explanation, and we definitely have a little better perspective on it over here anyway.
It looks like a little teapot kind of thing.
Yep. Very decorative. make our way back around and try to look at that valve gear a little bit.
This is another little piece here that's used to keep us out of trouble. When the engine hasn't been run for a while, a lot of the piping and plumbing in here will be cool, and the steam will condense in it, so we can get water in the plumbing on this. As I said earlier, that's really, really bad for the engine. So this has got a little float in it, and the water will drip down into here, condense down into here. Eventually, the float will rise, open the valve, and it ejects the water out into the exhaust in it.
Steam trap, designed to hold steam in and let condensate out. Very cool.
Yet another oiler. This one's actually for the cylinders on it. So before you start the engine, you need a little lubrication in the cylinders. So these two pipes here go off into the cylinders, and this is steam oil or cylinder oil. It's very, very heavyweight oil. So before we run the engine, we can open the valves on this thing, give this thing a couple of pumps, and squirt some cylinder oil into it. That makes it a little bit easier to get it running the first time.
Well, it's always great to see it run. Such an interesting mechanism. And really happy that people could join us this year electronically, you know, from around the world effectively, you know, real different look at everything here. We'd obviously much rather have everybody here in person to see these things you know, themselves, witness everything that's going on and so forth, but this is the second best thing. Well, thank you again, Mike. Thank you everybody out there. Hope everybody can get
Steam up.
Well, Steam Up 2020, right? Appreciate it.